Most of us think we know what space is. We've all seen the pictures, astronauts floating weightlessly above Earth, or those iconic footprints on the moon. We think of space as a destination, a place you visit and, most importantly, a place you can always come home from. But that comfortable idea is really just an illusion. It only covers our immediate cosmic neighborhood, the tiny, protected shoreline of a truly endless ocean. Welcome to the Science for Deep Sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. Out there, beyond the familiar glow of our moon, there's a point where everything we understand about travel, connection, and our place in the universe just breaks. It's not a wall or a barrier, but an invisible, unforgiving line. And once you cross it, you enter a fundamentally different realm. A place where Earth's gravity can't save you. You're in deep space. And you're on your own. What would you do if you found yourself on the other side of that line, with no way back? The illusion of space travel. When we think about human spaceflight, our minds pull up a highlight reel from the last 60+ years. We see Yuri Gagarin, the first person to glimpse the curve of the Earth, the Apollo astronauts planting a flag on the moon, the International Space Station making silent laps 250 miles above us. These moments feel epic, and they are. But in the grand scheme of things, they're also local. Extremely local. Here's the great, unspoken truth of our spacefaring age. Every single human who has ever gone to space has been on an invisible leash. We haven't truly left home, we've just stepped off the porch. The outer space humanity has explored in person begins at the Kármán line, only about 62 miles up. That's a shorter trip than driving from Los Angeles to San Diego. Astronauts on the ISS are still so close that the Earth dominates their view, a breathtaking panorama of continents and clouds. They're basically in a constant state of falling around the Earth, caught in a high-speed dance with its gravity. Even the incredible achievement of the Apollo missions, which sent humans 250,000 miles to the moon, didn't break this bond. The moon itself is our celestial companion, trapped in a gravitational waltz with our planet. The astronauts who walked on its surface were still firmly in Earth's gravitational sphere of influence, which is what made their return journey possible. Getting back from the moon, while a huge technical challenge, was basically a matter of falling back towards the biggest source of gravity in the neighborhood, home. This is how we've always approached space travel. It's a system built on the reassuring idea of a round trip. We burn a ton of energy to climb out of Earth's gravity well, do our thing, and then use that same gravity to pull us back. Every mission plan, every spacecraft, has been built on this gravitational tether. It's our safety line. But this safety net isn't infinite. We've been paddling in the shallows, looking out at the horizon, and mistaking the entire ocean for a calm bay. The real nature of deep space, the vast, indifferent, and profoundly alien environment that lies beyond, operates by a completely different set of rules. And to understand the point of no return, we first have to accept that everything we've done so far has just been the prologue. The invisible line. So, where does our cosmic backyard end and the true wilderness begin? There's no signpost, but there are a few important markers. For regulatory purposes, like managing radio frequencies, organizations like the International Telecommunication Union draw a line for deep space at 2 million kilometers, or about 1.2 million miles from Earth. Let that number sink in. The moon is about 384,000 kilometers away. So this official line is more than 5 times farther than any human has ever gone. All of human spaceflight history has taken place within the first 20% of the journey to this border. Now, that line is for communications, but the physics tells a similar story. The real gravitational tipping point, where the Sun's gravity starts to matter more than Earth's, is a bit closer, at around 1.5 million kilometers. This region is known as Earth's Hill Sphere, its personal bubble of gravitational dominance. Think of it like this: Earth's gravity is a gentle current pulling you back to shore. You can splash around, swim out a ways, and still feel that pull. The ISS is waiting in the shallows. The moon is a sandbar just offshore. But as you go further, you start to feel the tug of a much bigger force, the main current of the river. That powerful, relentless current is the gravity of the Sun. Once you cross that 1.5 to 2 million kilometer zone, you've waded out so far that the gentle pull of the shore is lost in the overwhelming flow of the river. You're no longer orbiting the Earth. You've effectively become your own tiny planet, orbiting the Sun. Your gravitational allegiance has shifted. This is why you can't just fly back. From this point on, returning home isn't about falling. It's about performing a complex orbital maneuver, like a tiny ship trying to chase down and rendezvous with a fast-moving planet. You'd need a massive amount of energy just to change your solar orbit to intersect with Earth's. We already have a pioneer living out on this frontier, the James Webb Space Telescope. It orbits the Sun at a special spot called Lagrange Point 2, about 1.5 million kilometers away. NASA already calls it a deep space mission. It's so far out that it was a one-way trip. No astronauts can ever go out to service it. It's our sentinel at the gateway to this new realm, proving that once you commit to the journey, you're truly out there. The journey outward, crossing the threshold. Imagine you're in the cockpit of a spacecraft, the Wanderer. Your mission: to be the first human to cross that invisible line. The engines ignite, pressing you back into your seat. Within minutes, the sky turns from blue to black. Earth hangs below you, a masterpiece of blue and white. You do a few final checkout orbits, and then Mission Control gives the go-ahead. The engines fire again, a long, sustained burn that flings you out of orbit and toward the moon. The blue marble shrinks behind you. The moon grows in your window, from a distant pearl to a colossal, cratered world of gray. For the Apollo astronauts, this was the farthest point. For you, it's just a waypoint. You slingshot around its far side, stealing a bit of its orbital energy to fling you even faster into the black. For a few tense minutes, communication with Earth goes silent. Then, as you swing back around, Earth reappears. But it's different now. It's small, no bigger than a marble held at arm's length. For days, you drift. The engines are silent. The moon shrinks behind you, quickly becoming just another bright star. Earth, too, continues to fade. It's the brightest star in your sky, a brilliant blue, but it's no longer a world. You can't make out continents anymore. It's just a light. This is where the psychological shift begins. In Earth orbit, the planet is an overwhelming presence. Out here, there is only the void. The starfield is absolute, a spray of diamond dust on black velvet, completely silent and indifferent. Your ship's clock ticks past 1.5 million kilometers, the lonely home of the Webb telescope. The communication delay is now several seconds long. Conversations become disjointed. And then, the moment arrives. Your navigation console flashes a simple notification. Distance from Earth, 2000 km. You've crossed the line. Nothing explodes. No alarms sound. The view is exactly the same as it was a minute ago. But everything has changed. The final, thinnest strand of Earth's gravitational leash has snapped. You are now, officially, a solitary traveler in orbit around the Sun. A deep, primal feeling settles in your gut. It's the feeling of being untethered. You look at the bright blue star in the viewport. That's Earth. It's no longer pulling you home. To get back, you'd have to burn a huge portion of your fuel just to start the journey. The way back isn't the default path anymore. The default path is to just keep going, forever. The point of no return isn't a place you arrive at, it's a realization that dawns on you, long after you've already passed it. A new reality. The rules have changed. The second you're in deep space, the rulebook for space travel gets torn up. The two things that change most dramatically are communication and propulsion. First, communication. We're used to instant connection. But even light has a speed limit, and in deep space, that limit is a crushing barrier. At the 2 million kilometer line, a round trip for a radio signal takes about 13 seconds. Awkward, but manageable. But what if you keep going toward Mars? At its closest, Mars is 55 million kilometers away. A simple, "Houston, we have a problem," would take over 3 minutes to reach Earth. The reply, "Say again?" would take another 3 minutes to get back. A 6-minute delay for 2 short sentences. If Earth and Mars are on opposite sides of the Sun, that round trip can take up to 45 minutes. This is the tyranny of light speed. Real-time control is impossible. You can't have a conversation. You send messages into the black, and then you wait. And wait. The psychological effect is a form of isolation more complete than anything on Earth. You're not just separated by distance, but by time itself. The second new rule is about getting home. This isn't like a road trip where you can just turn the car around. Spacecraft are slaves to something called the tyranny of the rocket equation. The short version is, to change your speed, you need fuel. But that fuel has weight. And to push that extra weight, you need even more fuel. It's an exponential nightmare. To get home from deep space, you couldn't just fall back to Earth. First, you'd have to hit the brakes, firing your engines to cancel out your enormous orbital velocity around the Sun. Then, you'd need another massive engine burn to push your ship onto a new path that would perfectly intersect with Earth's orbit at some precise moment in the future. This means you have to carry all that fuel with you, fuel for the trip out, fuel to slow down, and fuel for the trip back. With today's technology, a round trip to Mars is already at the absolute edge of what we can do. Any journey beyond that is basically a one-way trip by default. Our robotic probes, like Voyager, cheat. They use gravity assists, slingshotting around giant planets to steal orbital energy and fling themselves onward. But that only works when you have a Jupiter or a Saturn in the right place at the right time. For a human crew lost in the emptiness between planets, there are no gas stations and no helping hands. Once the fuel is gone, your fate is sealed. Adrift in the emptiness, the existential void. The technical challenges are huge, but maybe they're not the biggest problem. The truly insurmountable barrier might be the one inside our own heads. What happens to the human mind when it's truly, irrevocably cut off from home? The psychological strain of spaceflight is something space agencies already lose sleep over. On the ISS, astronauts have video calls with family, a packed work schedule, and the constant, reassuring sight of Earth. Even then, it's tough. Now, amplify that isolation by 1,000. On a trip into deep space, the awe would eventually fade into a profound, crushing monotony. Outside your window, the scenery would stop changing. The stars don't twinkle. There's no weather, no birds, no sunrise or sunset. Just a perfect, static, and silent blackness. Your entire universe becomes a tiny metal can, humming with the sound of life support. This is an environment of extreme sensory deprivation. Our brains evolved to process the feeling of wind, the smell of rain, the sounds of a city. Take all that away, and what's left is just you and your own thoughts. Studies in isolated environments on Earth, like Antarctic research stations, show people can suffer from anxiety, depression, and cognitive issues. And those people can at least step outside for a walk. For a deep space traveler, there is no outside. There is only the ship and the void. All of human history, every war, every love song, every person you've ever known is on that tiny, distant dot of light. This is the source of the overview effect, the cognitive shift many astronauts feel when they see Earth from orbit. But they experience that from the safety of Earth's embrace. What happens when you push that effect to its extreme? Does it become a deep space effect? A feeling not of connection, but of radical, terrifying disconnection? The time lag in communication would make it worse. Getting a message from a loved one about something that happened 12 hours ago would be a painful reminder that you're living in their future, and they are living in your past. You're a ghost. This existential dread might be the true point of no return. Not a line in space, but a line in the mind. At what point does a brain evolved for a vibrant, social planet simply break under the strain of absolute cosmic indifference? The farthest frontier, interstellar space. But what if we went even further? What if we left the solar system entirely and pushed into the true abyss, the space between the stars? This isn't science fiction. We've already done it. In 1977, two spacecraft, Voyager 1 and Voyager 2, left Earth. After giving us a spectacular tour of the outer planets, they just kept going. For decades, they traveled through a region dominated by the solar wind, a bubble of particles from our sun called the heliosphere. This bubble shields our solar system from the harsh radiation of deep interstellar space. Then, in August 2012, something amazing happened. Voyager 1, now billions of miles out, detected a massive change. The solar particles vanished, and harsh cosmic rays from outside our solar system flooded its sensors. The data was clear. It had crossed the heliopause. It had left the solar system and entered interstellar space. Its twin, Voyager 2, followed it out in 2018. As of today, Voyager 1 is over 26 billion kilometers away. Its faint radio signal, traveling at the speed of light, takes nearly 24 hours to reach us. A single, "hello," and "I'm okay" exchange now takes almost 2 full days. Their journey is the ultimate one-way trip. Their plutonium power sources are slowly decaying. NASA engineers have managed power so well that they're now expected to keep at least one instrument running into the early 2030s. But eventually, perhaps not long after that, their power will fail. One by one, they will fall silent. They will become ghost ships, continuing their journey without us. But they won't be empty. Attached to the side of each probe is a golden record. It's a message in a bottle, thrown into the cosmic ocean. It contains greetings in 55 languages, the music of Bach and Chuck Berry, and the brainwaves of a woman in love. It's a testament to a species that, while stuck on one fragile planet, dared to look up at the infinite dark and send a piece of itself into eternity. The fate of the Voyager probes is a poignant reminder of both our ambition and our limits. They will never come home. Journeys to the edge of what's possible redefine our place in the universe. They are stories of science, engineering, and the unyielding human spirit to see what's over the next hill. If these voyages into the great unknown fascinate you, consider subscribing to keep exploring the biggest questions with us.
Your support allows us to keep asking, what if? We started with a question, what if deep space has no way back? We've traveled across an invisible line where the rules of existence change, where communication slows to a crawl, return becomes a near impossibility, and the mind itself becomes the most fragile piece of hardware. That line, somewhere out past the moon, is more than a distance. It's a philosophical boundary. It separates our home from an indifferent universe that operates on a scale our minds can barely grasp. The Voyager probes have shown us that crossing this boundary is possible. They are our silent emissaries, carrying our music and our hope into the void. But we have never sent a person across that line. We've never asked a human being to look back at the pale blue dot and know, with bone-deep certainty, that they are no longer gravitationally tied to it. So, here's a final thought. Is this point of no return a cosmic warning sign, telling us that some distances are just too vast for creatures like us? Or is it simply the next frontier, a challenge to our courage? What does it say about us that when faced with an eternal, one-way journey into the unknown, a part of us doesn't feel fear, but instead feels a single, irresistible urge to go? Part 2. Why distance changes everything? It is easy to think of distance as a simple thing. A number on a map, a longer drive, a longer flight, a little more time between where you are and where you want to be. Here on Earth, distance usually feels like an inconvenience, not a verdict. If something is far away, you leave earlier. If the road is long, you bring more food, more patience, maybe a second driver. Distance stretches the journey, but it does not usually change the meaning of the journey itself. In deep space, that comfortable idea quietly falls apart. Because out there, distance is not just more of the same. It is not just a longer version of a familiar trip. It is the thing that changes every other rule. It changes how long help takes to arrive. It changes how much fuel you need, how much food you must carry, how much time your body must endure, how much silence your mind must survive. It changes what the word return even means. And that may be the first hard truth hidden inside the dream of space travel. The universe does not need a wall to keep you from coming home. It does not need a trap, or a storm, or some violent cosmic force. Sometimes, all it needs is distance. Pure, silent, indifferent distance. Imagine a spacecraft already far beyond the moon. Earth is still there, still bright, still beautiful, but it no longer fills the sky the way it once did. It has begun to shrink into an object rather than a world, a destination rather than a home. And that shift matters more than it seems. Because once home becomes a small thing in a very large darkness, your whole relationship with reality changes. You are no longer moving through a familiar neighborhood. You are stepping into a scale that the human mind was never designed to feel. The problem begins with how badly our intuition fails. We are creatures of villages and roads, coastlines and weather. Even our biggest earthly distances are still wrapped inside a world that supports us. On Earth, there is air to breathe, gravity to stand on, water to drink, and other people not too impossibly far away. Even in the middle of an ocean, you are still on a planet that can keep you alive. Even in the most remote desert, the sky above you is still your sky. Space offers none of that comfort. It offers distance without support, distance without atmosphere, distance without roads, without shelter, without rescue stations, without any natural margin for error. If your car breaks down on a highway, it is a problem. If your ship suffers a major failure halfway to another planet, it becomes something else entirely. Not a delay, not an inconvenience. A crisis unfolding inside an emptiness that does not care whether you solve it. That is why space distance is so much more severe than earthly distance. It is not just separation. It is separation combined with total environmental hostility. To understand how dramatic this becomes, it helps to slow down and look at the numbers the way the universe presents them, not the way our daily lives train us to feel them. The International Space Station, for all its grandeur, is only a few hundred kilometers above Earth. In cosmic terms, that is almost touching. The Moon, which feels unimaginably far in ordinary life, is about 384,000 kilometers away. Light, the fastest thing in the universe, takes only about 1.3 seconds to travel from the Moon to Earth. That still feels close enough to belong to the same family of places. But once you begin moving into the broader solar system, the scale changes so quickly that familiar language starts to lose its grip. Mars, at its closest, is tens of millions of kilometers away. At its farthest, it can be hundreds of millions. Jupiter sits hundreds of millions of kilometers farther out still. Neptune is billions of kilometers away. And between each of these worlds is not a crowded corridor of useful material, but mostly nothing. Just vast, cold intervals of almost perfect emptiness. This is where distance stops being intuitive and starts becoming oppressive. A trip from one city to another feels real to us because we can imagine the road between them. A trip from Earth to deep space is different. because there is almost nothing to imagine in between. No landmarks, no rest stops, no villages, no mountains on the horizon, just a lengthening absence. And absence has consequences. The first consequence is time, though not yet in the deeper sense we will come to later. At even modest cosmic distances, communication itself becomes slow enough to change how a mission lives from moment to moment. Near Earth, control can still feel immediate. At the Moon, the delay is short enough to tolerate. But farther out, conversation begins to dissolve. A message to Mars can take several minutes one way, depending on where Earth and Mars are in their orbits. By the time you send a question and hear the answer, the problem on board may already have evolved. The farther you go, the less Earth is a live partner and the more it becomes a distant archive. That matters because on Earth, help is often just another person plus a little time. A phone call, a mechanic, a doctor, a second opinion. In deep space, distance slowly erases that option. Advice arrives late. Rescue arrives later still, if it can arrive at all. Imagine a crew noticing a leak, a failed pump, or a damaged system. Near Earth, engineers could guide them almost in real time, and replacement parts might be sent quickly enough to matter. But far from Earth, a small technical failure can begin to change character. It is no longer just a repair problem. It becomes a question of whether the ship can continue to be its own factory, hospital, storage room, and shelter all at once. That is one of the quiet cruelties of deep space. Distance turns small mistakes into large ones, and large ones into final ones. A loose seal, a contaminated waterline, a malfunction in temperature control. Here at home, each of those sounds manageable. Somewhere beyond Earth's comfortable reach, each one becomes a test of whether the mission still has enough redundancy left to remain alive. The distance does not create the fault. It simply removes all the easy ways of surviving it. And that changes how every kilogram on board must be thought about. When people imagine a deep space mission, it is natural to think mostly about the destination, the planet, the moon, the dramatic arrival. But the reality is far more humble and far more difficult. A mission is not just moving people through space. It is moving a sealed life-supporting ecosystem through a vacuum. Every breath, every sip of water, every meal, every battery cycle, every filter, every valve, every backup component must either continue working or be replaced by something already carried on the ship. Distance turns all of that into a slow arithmetic of survival. The farther you go, the more of your own world you must carry with you. Not only the crew, but the conditions that allow the crew to remain human. Air must be recycled. Water must be recovered. Waste must be managed. Heat must be controlled. Electronics must survive radiation and time. Mechanical systems must continue functioning in a place where there are no stores, no warehouses, no emergency delivery routes, no practical way to step outside and fix things the way you would repair something on Earth. The ship has to become a tiny island of order carried through a sea of nothing. And the larger the distance, the longer that island must preserve itself. This is where distance begins to feel almost philosophical. Because what we call a journey on Earth is usually still a movement within a living system. A person can go far, but still remain surrounded by Earth's support. A deep space traveler is different. The traveler is not moving within the system anymore. The traveler is dragging a miniature version of the system along with them and hoping it lasts long enough to bring them back. That hope becomes thinner with every added million kilometers. It is also important to understand that distance in space is not static in the way earthly distance often seems. Earth is not sitting still, waiting faithfully to receive you when you decide to return. It is moving. The spacecraft is moving. The sun's gravity governs both. So when you leave Earth, you are not stepping away from a parked house. You are leaving one moving object and entering a much larger celestial choreography. Coming home later is not as simple as reversing direction. Home has kept going. Even without getting too technical, that changes everything. If you travel across a field and want to return to your starting point, the field is still there, and your starting point is still where you left it. In deep space, the entire system is dynamic. Earth continues orbiting the Sun at tremendous speed. A returning ship must not only travel back across distance, but meet a moving planet at the right place and the right time. Distance makes that task more fragile, more exact, and much less forgiving. So the farther you go, the more return becomes a matter of precision rather than mere intention. You can already sense the shape of the deeper problem now. Distance is not just about how far away Earth becomes. It is about how many layers of difficulty begin stacking on top of one another as Earth fades. Communication delay, rescue impossibility, supply burden, system fragility, orbital timing, psychological separation, energy demand. All of them grow with distance. All of them feed one another. And perhaps the most deceptive part is that space does not look dangerous in the way we instinctively expect danger to look. A storm on Earth announces itself. A wave can be seen. A fire can be smelled. A cliff looks like a cliff. But deep space can seem calm, even gentle. A black sky. A few stars. Sunlight on metal. A planet glowing quietly in the distance. It looks still. It looks almost peaceful. Yet that peace is part of the trap. Because the danger is not usually something rushing toward you. The danger is the quiet accumulation of separation. The fact that help is too far away. The fact that Earth is no longer a place you can simply fall back toward. The fact that every hour spent moving outward deepens the cost of every future correction. Distance behaves less like an attacker and more like a slow verdict, one that becomes harder to appeal with every passing day. This is why the romantic language of exploration can sometimes hide what is really happening. We speak of voyaging, discovering, crossing the darkness. And those words are beautiful. But beneath them is a harsher reality. Deep space does not merely invite courage. It demands independence at a scale humanity has barely ever had to practice. A traveler in deep space cannot rely on the assumptions that shaped all earlier human journeys. There may be no quick return, no quick rescue, no quick answer. Only the ship, the crew, the math, and the distance. Even the emotional meaning of Earth begins to change under that pressure. From orbit, Earth feels close enough to protect. From the moon, it still looks like a world you belong to. But deep in space, Earth slowly changes into a memory you can still see. A bright point. A cherished direction. A place that exists with all its oceans, forests, cities, children, music, language, weather, and ordinary life, but is now so far away that even your longing cannot shorten the journey. That may be one of the strangest facts of all. Distance can turn home into something emotionally vivid and physically unreachable at the same time. And that is why distance matters so much more than it first appears. Because return is not defeated only by explosions or disasters. It can be defeated by scale itself. By the simple truth that beyond a certain point, a ship is no longer on a trip where coming back is the default ending. It is on a mission where every extra stretch of outward movement must later be paid for in time, resources, accuracy, endurance, and luck. If the quiet scale of the universe fascinates you, and these slow journeys through science help you settle into the night, you are always welcome to subscribe and stay for the next one. And if you feel like sharing, I always like knowing where in the world these thoughts are reaching you tonight. There is another reason this subject feels so haunting. On Earth, we are used to believing that enough determination can solve almost anything. Work harder. Go farther. Push through. But deep space does not negotiate on those terms. It is not impressed by desire. It does not shrink because we are brave. It does not grow kinder because we miss home. It only remains what it is, enormous beyond instinct, sparse beyond comfort, and patient beyond imagination. So when people ask why returning from deep space may never be possible, one of the deepest answers is also one of the simplest. Because space is not merely far. It is far in a way that changes all the surrounding rules. Far enough that speed becomes insufficient. Far enough that help becomes irrelevant. Far enough that supplies become a burden, timing becomes delicate, and home becomes a moving target inside a vast celestial machine. Distance, in other words, is not just one problem among many. It is the condition that makes all the other problems harder. And once you truly feel that, once you let the scale settle in, the universe begins to look different. Not smaller, not crueler, just more honest. The moon no longer feels like the edge of the adventure. Mars no longer feels like a bold but ordinary extension of travel. The outer solar system no longer feels like a set of places waiting politely to be visited. Everything becomes what it always was, staggeringly far apart, stitched together by gravity and light, but not by convenience. The truth is that deep space may not keep us away by force. It may keep us away by mathematics, by duration, by emptiness, by the fact that a human life, and a human machine, can only stretch so far before the distance itself becomes the mission's true commander. And that is the threshold we begin to approach the moment we leave Earth behind. Because once the gap becomes large enough, the journey outward is no longer the greatest question. The way back is. Part 3. The problem of fuel in empty space. At first, the problem seems almost too ordinary to be frightening. Fuel. Not a black hole. Not a violent explosion. Not some mysterious edge of the universe. Just fuel. The same basic idea that decides whether a car can make it to the next town, whether a plane can cross an ocean, whether a ship can survive a long crossing. On Earth, fuel feels like a practical matter. Important, yes, but manageable. You fill the tank. You plan the route. You stop when you need to. It belongs to the world of logistics, not existential dread. But in deep space, fuel becomes something else. It becomes one of the quiet, unforgiving reasons that returning home may simply stop being possible. Because out there, fuel is not just what moves you forward. It is what decides whether your journey can ever be reversed at all. And the farther you go, the more fuel you need to come back. But the more fuel you carry, the heavier your spacecraft becomes. And the heavier it becomes, the more fuel you need just to move that extra fuel. That is the trap. It is one of the strangest and most elegant traps in all of physics. The machine needs fuel to move, but the fuel is also part of what must be moved. And when the distances become truly large, that simple fact begins to dominate everything. Imagine standing beside a campfire at night, somewhere far from the city. The air is still. The dark around you feels immense. You toss a small stick into the flames, and the fire answers immediately. A little more light, a little more heat. Cause and effect. Clean and simple. Rockets do not work like that. A rocket does not burn fuel merely to release energy. It burns fuel to throw mass backward, so the spacecraft can move forward. The flame itself is not the point. The exhaust is. This matters because every change in speed in space comes at a cost. And that cost is not measured only in power, but in reaction mass. If you want to speed up, you must throw something behind you. If you want to slow down, you must again throw something behind you, just in a different orientation. If you want to turn around and come home, you must spend fuel not once, but repeatedly, shaping your path through a gravitational system that never stops moving. That sounds manageable when phrased in a sentence. But the numbers hidden inside that sentence are brutal. A spacecraft leaving Earth must first climb out of Earth's gravity well. That alone takes an enormous amount of energy. Even reaching low Earth orbit is already one of the most demanding parts of any mission. The reason rockets look so absurdly large compared to the tiny capsule or payload on top is that most of the rocket is not crew space, or instruments, or supplies. Most of it is propellant. A launch vehicle is, in a very real sense, a huge tower of fuel built to push a comparatively small useful object into space. The Saturn V, the giant rocket that sent astronauts to the moon, stood taller than a 30-story building. It looked like a monument to engineering, and it was. But in another sense, it was also a monument to this problem. Almost all of its mass at liftoff was fuel. The crew cabin, the thing we emotionally think of as the mission, was a tiny fraction of the whole machine. The rest existed largely to get that fraction moving fast enough to matter. That is the first clue that fuel is not a minor technical detail. It is the architecture of the mission itself. And once you begin thinking about a return from deep space, the difficulty compounds in a way that feels almost unfair. Because it is not enough to bring fuel for the way out. You must also bring fuel for slowing down, fuel for course corrections, fuel for surviving emergencies, and fuel for the way back. And all of that return fuel must itself be carried during the outward journey, which means the ship starts heavier, which means the ship needs even more fuel just to carry the return fuel it will later need. This is the heart of the rocket equation, though you do not need to memorize the formula to feel its meaning. It tells us that rocket travel becomes punishingly expensive in mass the more velocity change, or delta V, you ask for. Each extra demand does not add difficulty in a neat, linear way. It multiplies it. A little more speed can require a lot more propellant. A lot more speed can require truly absurd amounts. On Earth, we are used to tools that scale in ways that feel reasonable. A slightly bigger truck can carry a slightly bigger load. A slightly larger battery can power a device a little longer. Rockets are not so polite. Ask them for too much, and they begin to punish you mathematically. It helps to picture a traveler preparing for a very long winter crossing. He loads food onto a sled, but the more food he loads, the heavier the sled becomes. So he decides he needs more food to sustain the extra effort of pulling the heavier sled. But that added food makes the sled even heavier still, so he must add more food again. You can feel the absurdity rising. At some point, the journey is no longer about the traveler reaching the destination. It is about the traveler trying to carry the burden created by his attempt to prepare for the journey. A deep space spacecraft faces a version of that problem, except the mathematics are harsher, and the environment offers no mercy. This is why so many robotic missions are one way by design. It is not because engineers forgot to imagine a return. It is because return costs mass, and mass costs fuel, and fuel costs even more mass. If your mission's goal can be achieved by sending an instrument and gathering data without bringing it home, that is usually the more realistic path. The spacecraft can be lighter, simpler, cheaper, and more capable at the one thing it was meant to do. Humans, of course, are different. We do not like one-way missions. Machines can be sacrificed to the void. People carry a different emotional and moral weight. We instinctively want a return plan. We want the story to curve back toward home. But physics does not care about narrative symmetry. It cares about momentum, mass ratios, exhaust velocity, and timing. And those things become merciless once the distances become deep enough. For a journey near Earth, or even to the Moon, there are still ways to work with the problem. The Moon is relatively close. The timing can be planned. Earth remains a strong gravitational partner in the mission. Apollo was enormously difficult, but it still happened within a part of space where return remained barely inside the realm of the manageable. Even then, the engineering margins were tight, the planning was exacting, and the machine required to do it was gigantic. Now imagine stretching that logic outward. To Mars, the challenge becomes far greater. To the outer planets, it becomes staggering. To deep space beyond the comfortable boundaries of our planetary neighborhood, it starts to drift into a different category entirely. Not impossible in the poetic sense. Impossible in the operational sense. The kind of impossible that emerges when too many requirements begin crushing the same mission from different directions. A ship going far outward and then returning home must remain a functioning habitat for an extremely long time. That means life support, water recycling, radiation shielding, spare parts, medical equipment, food systems, power generation. redundancy for critical failures. All of this adds mass. Then, layered on top of that, you must still solve propulsion. And propulsion itself adds mass in the form of engines, tanks, structural support, insulation, control systems, and propellant. It becomes a kind of stacking burden. Each solution makes the vehicle heavier, and the heavier vehicle makes propulsion harder. You start to see why the dream of a long round-trip deep space mission begins to feel less like building a ship and more like trying to launch a tiny, self-sustaining world. And then comes another painful twist. Fuel is useful only if it remains with you in the right form at the right time. A road trip on Earth can rely on infrastructure. If a driver does not want to carry all the gasoline for a 1,000-mile journey at once, there is no need. The world provides stations along the route. The burden is distributed across civilization. Space offers no such kindness. No refueling depots drift naturally between the planets. No quiet outposts wait in the black with fresh tanks and spare hardware. Every kilogram you might need later must be launched earlier, stored safely, protected from leaks, protected from boil-off if it is cryogenic, and still remain available after months or years in an unforgiving environment. And storage itself is not a trivial matter. Some of the most powerful rocket fuels are difficult to keep stable for long periods. Cryogenic propellants, such as liquid hydrogen and liquid oxygen, must be kept extremely cold. In the vacuum of space, with sunlight, shadow, time, and system limits all working against you, that is not easy. Keeping fuels ready for a return journey after a long mission is not just a matter of putting them in a tank and trusting the tank. It is an ongoing engineering challenge. So even when a fuel looks promising on paper, reality asks a quieter question. Can you carry it, preserve it, and depend on it when you are unimaginably far from help? That question becomes sharper in deep space because everything must stay reliable for longer than human technology usually enjoys staying perfect. Even small inefficiencies grow teeth over time. A slow leak that would be annoying on Earth becomes catastrophic in space. Thermal cycling can weaken materials. Radiation can degrade electronics. Valves can stick. Sensors can drift. Seals can age. A mission depending on a future burn to come home is not just trusting its fuel mass. It is trusting the survival of an entire propulsion system across a long exile in the void. And if that burn does not happen when needed, there may be no second chance. This is also why, "just turn around," is one of the most misleading phrases anyone can imagine about space travel. In ordinary language, turning around sounds simple. In space, it is rarely simple. A spacecraft is not driving through emptiness in the casual way a car drives through a night road. It is moving within the gravity of the sun, already carrying enormous orbital speed just by virtue of being part of the solar system. To come home, it must carefully reshape that motion. Sometimes it must slow relative to one body, speed relative to another, arrive at a narrow window, and then survive whatever comes next. All of that requires fuel, not as an abstract concept, but as precise, reserved, usable capability. People sometimes imagine that once you are out in space, motion should be easy because there is no air resistance. And in one narrow sense, that is true. A spacecraft can coast beautifully. It does not need constant fuel to keep moving once it has velocity. But that is exactly why returning is hard. Coasting preserves your existing path. It does not grant you a new one. If your path takes you farther and farther from Earth, then continuing to do nothing may simply mean continuing to leave. Coasting is easy. Changing destiny is expensive. There are some clever ways around parts of the fuel problem, and humanity has used them beautifully. One of the most elegant is the gravity assist. Instead of spending large amounts of propellant to speed up or redirect a spacecraft, mission planners can send it close to a planet and use the planet's gravity like a moving sling. The Voyager probes used this method to cross the outer solar system with a grace that still feels almost magical. They stole tiny amounts of momentum from giant planets and used that gift to keep going outward. But gravity assists are not free miracles. They depend on where the planets are, when you launch, where you need to go, and what kind of mission you are flying. They are like rare winds or currents in an ocean that only exist at certain times in certain places. You cannot assume they will solve every return problem, especially for a crewed mission that must prioritize safety, timing, shielding, supplies, and survivability. And even when gravity helps, it does not erase the need for propulsion. It only reduces part of the burden. There are also engines that use fuel more efficiently than traditional chemical rockets. Ion engines, for example, can produce a gentle but very efficient push for long durations. They are wonderful for certain robotic missions. Over months or years, that faint continuous thrust can reshape a spacecraft's trajectory with remarkable economy. But ion engines are weak in raw thrust. They are not the kind of thing you rely on to launch humans from Earth or rapidly rescue a failing mission. They are patient tools, not dramatic saviors. Nuclear propulsion has long been imagined as a possible step forward. In theory, it could offer better performance, allowing ships to carry less propellant for the same mission or travel faster within the solar system. Some designs have been studied for decades. Even more speculative concepts, like fusion drives, appear in the dreams of future engineers and science fiction writers alike. And perhaps one day, some of those ideas will mature into real systems. But here, in the calmer light of what we can truly count on now, they remain mostly future doors, not present bridges. So for the foreseeable reality of spaceflight, fuel remains the blunt, controlling truth. It decides what can be launched, what can be accelerated, what can be slowed, what can be brought back, and it does so with very little sentiment. This has a quiet emotional consequence too, because when people think about returning from deep space, they often imagine the human desire to come home as the central force in the story. The courage of the crew, the ingenuity of the engineers, the urgency of the mission, and all of that matters. It matters profoundly. But beneath those noble human things lies a colder foundation. The amount of usable propellant, the performance of the engine, the mass ratio of the vehicle, the timing of the burn. In other words, the emotional arc of the mission depends on a very unromantic arithmetic. A crew could miss Earth with all the longing in the world, and the universe would still ask the same question. Did you bring enough fuel? Did it survive the trip? Can your engine still deliver exactly what is needed, exactly when it is needed? If the answer is no, then home does not become less loved. It simply becomes unreachable. If these slow explorations of the universe help you settle into the night, you can always subscribe and return for more. And if you'd like, you can leave a quiet comment about where in the world you're listening from tonight. I always enjoy imagining these ideas drifting out into real rooms, real cities, real sleepless hours. Perhaps that is the strangest contrast of all. Here on Earth, we live in a world full of replenishment. Morning follows night. Food grows again. Rivers flow again. Roads remain. Power can be restored. Tanks can be refilled. But a deep space mission is like carrying a candle through an endless cave. Every ounce of wax matters. Every flicker matters. And if you realize halfway through that you needed more than you brought, there may be no way to bargain with the darkness. This is why fuel in deep space is not merely a technical challenge. It is a form of commitment. The moment you leave, you are making promises to the future version of yourself. Promises that your stored energy will still exist when you need it. That your engines will still answer. That your calculations were right. That the road home, if it exists at all, can still be paid for. And the farther you go, the more fragile those promises become. So when we ask why returning from deep space may never be possible, fuel stands quietly near the center of the answer. Not because space is empty, but because emptiness gives you nothing for free. No atmosphere to breathe. No stations to refuel. No natural mechanism to reverse your path. Only the propellant you launched with, the physics you obey, and the long consequences of every decision made before you left Earth. Distance makes the journey longer, but fuel decides whether the journey can remain a round trip. And once the numbers grow large enough, once the ship must carry not only its crew and its shelter but also the enormous burden of its own future return, something subtle happens. The mission stops looking like an expedition and starts looking like an equation with no graceful solution. Not because humanity lacks bravery, not because the stars are hostile in some dramatic way, but because the cost of coming back keeps rising until the ship is carrying too much of tomorrow to survive today. That is the real cruelty of the fuel problem. To come home from deep space, you must bring home with you from the very beginning, in the form of mass, possibility, and stored force. And at some point, the amount required becomes so great that the journey itself begins to collapse under the weight of its own return plan. So the outward path remains open. In a sense, it always does. With enough will, enough engineering, enough sacrifice, we may keep sending machines and perhaps one day even people farther into the dark. But the way back is harder. Because in deep space, every dream of return must first survive the oldest and simplest demand any voyage has ever known. You must still have enough left to come home. Part 4. Why space doesn't help you come home. There is a quiet assumption hiding inside almost every human journey. That the world, in some way, will help you back. A road remains under the tires. A coastline can be followed home. A river can be traveled in reverse. Even the sky, for all its dangers, still belongs to a planet filled with air, weather, radio towers, runways, and people. Here on Earth, the world is not neutral. It supports return. It gives you surfaces, signals, landmarks, resistance, shelter, and second chances. It may not always be kind, but it is still a place built around the possibility of coming back. Space is not like that. And this is one of the hardest things to truly feel. Because when we picture space, we often picture freedom. Endless openness. No traffic. No terrain. No atmosphere to slow you down. It seems, at first glance, like the perfect place to travel. Just point the ship, fire the engines, and drift through a beautiful black sea of stars. But that image hides the deeper reality. Because space does not help you move in the way Earth helps you move. And it certainly does not help you return. It offers no road, no current that reliably bends toward home, no natural cushion for your mistakes, no silent system working in the background to keep you alive and oriented. If Earth is a world that gently supports motion, space is a vacuum that simply allows motion to continue, whether that motion is useful to you or not. And that difference may be the beginning of the whole tragedy. A spacecraft in deep space can still move, of course. In some ways, it moves very well. There is no air resistance to fight, no weather to punch through. Once you are already in motion, you can coast for a very long time. That sounds like an advantage, and in one narrow sense, it is. But this is also where intuition can become dangerous. Because the ability to keep moving is not the same thing as the ability to go where you need to go. And it is certainly not the same thing as being able to come back. On Earth, motion is full of friction, but friction is not always an enemy. Friction helps you stop. It helps you turn. It helps a shoe grip the ground and a wheel grip the road. Air may resist a plane, but air also allows wings to work. Water may slow a ship, but water also holds the ship up. Again and again, the environment does two things at once. It resists you, but it also supports you. It gives you something to work with. Space gives you almost nothing to work with. That is the heart of this part of the story. Deep space is not merely far away. It is mechanically unhelpful. It does not cooperate with human needs. It does not provide the ordinary physical feedback that makes travel feel manageable on Earth. If you drift in the wrong direction, nothing in the environment leans in and gently corrects you. If you begin to rotate, nothing naturally damps that motion. If your path slowly stops making sense, the vacuum does not care. It will happily let you continue making the same mistake forever. This is why the image of a spaceship, turning around and heading home, can be so misleading. It sounds easy because the phrase comes from Earth. It belongs to roads and vehicles and landscapes we know how to imagine. But in deep space, there is no road to reverse on. There is only trajectory. And trajectory is not a preference. It is a commitment. Imagine a tiny boat drifting on a still lake at night. If it begins moving away from the shore, the person inside can paddle back. There is water beneath the boat. The water gives the paddle something to push against. The environment itself makes return physically possible. Now imagine taking away the water. No lake, no air, no ground, no medium at all. A paddle becomes meaningless. Motion still exists, but the easy human methods of changing motion disappear. That is closer to the truth of space. The only way to meaningfully change your path in deep space is to carry your own means of doing it, your own propellant, your own power, your own navigational precision, your own life support, your own timing. The environment contributes almost nothing. It does not refill you. It does not hold you up. It does not guide you home. And in some cases, it actively works against the idea of return, not through drama, but through indifference. One reason is gravity, though not in the simple way we often imagine it. People sometimes think of deep space as a place where gravity disappears. That is not really true. Gravity is everywhere. The sun still dominates the solar system. Planets pull. Moons pull. Even small bodies exert tiny influences. The problem is not the absence of gravity. The problem is that gravity in deep space does not act like a convenient hand drawing you back to Earth. Once you are far enough away, Earth is no longer the central force shaping your motion. You are no longer loosely tied to a local home. You are a small object moving in the larger architecture of the solar system. That means Earth stops being your default destination. And that is a profound shift. During the low Earth orbit mission, the Earth is always there beneath you, massive and immediate. The path home is still wrapped around the planet's presence. During the Apollo missions, although the journey was extraordinary, the Earth-Moon system still defined the mission. But in deep space, the sun becomes the main organizer. Your spacecraft is no longer living inside a small local neighborhood in the same way. It is part of a much larger orbital dance. And in that dance, Earth is not waiting quietly in one place. It is moving. So even if your ship remains perfectly healthy, even if your crew remains calm, even if nothing breaks, the environment is still not helping you come home. It is just carrying everything onward according to the rules of celestial mechanics. You are not on a marked route with a simple return lane. You are on a moving path inside a vast clockwork, and if you want to meet Earth again, you must do so by precise timing and deliberate force. That is very different from falling back. And perhaps this is where a lot of people underestimate the true loneliness of deep space. Not the emotional loneliness yet, though that matters too. A more physical loneliness. The loneliness of being in a place where the universe does not provide infrastructure. A desert on Earth is lonely, but the desert still has gravity, air, temperature gradients, sunlight shaped by an atmosphere, and a horizon your senses can read. Deep space gives you almost none of that. There is no natural up or down, no wind, no sound outside the hull, no tactile sense of progress, no passing scenery to confirm your motion in the way a moving landscape confirms it on Earth. In fact, some of the most unsettling aspects of space come from this lack of ordinary feedback. A spacecraft can be traveling at extraordinary speed and still feel motionless inside. No vibration from tires. No sway from ocean waves. No roar of air rushing past the windows. Just stillness. A sealed cabin. A hum of systems. The knowledge, but not the feeling, that you are moving at thousands of kilometers per hour through a region that is not helping you in any human way. This matters because return is not just an engineering problem. It is also a problem of orientation, timing, and trust. Humans like environments that talk back. We like to feel the road under us, hear the engine change, see the shape of the land, notice the weather shifting. These things make travel intuitive. Deep space strips that intuition away. It gives you equations, instruments, and silence. And if your instruments fail, the silence remains. There is another earthly assumption that space quietly destroys. The idea that empty means easy. On Earth, emptiness can sound desirable. An empty road is a smooth drive. An empty airport is a relief. An empty beach is peaceful. We are used to thinking that fewer obstacles make movement easier. So a place with almost nothing in it sounds, at first, like a traveler's dream. But in deep space, empty often means unsupported. There is no air to brake against when you need to shed speed. On Earth, re-entry vehicles use the atmosphere almost like a giant invisible hand. The atmosphere punishes them with heat, yes, but it also slows them. It gives them something to work against. Parachutes become possible only because there is air. Wings become useful only because there is air. Even a rough landing is still a negotiation with a medium that can help remove energy from the vehicle. In deep space, there is no such medium. If you are carrying too much speed relative to where you want to go, nothing outside the spacecraft is naturally helping you solve that. You must solve it yourself, with your own engines and your own stored energy. This is one reason why arrival and return are so difficult in space missions. Not just departure. Leaving Earth is expensive, but so is slowing down somewhere else. If you wanted to visit another world and then come home, you would need a way to arrive safely, a way to leave again, and a way to shape your return. The vacuum does not soften any of those tasks. It simply waits to see whether your machine can do them unaided. The emptiness between worlds is also too empty to rescue you in the ordinary human sense. A sailor in the ocean can, at least in principle, be found by another ship. A lost hiker can be searched for by helicopter. A broken plane can radio distress signals through an atmosphere full of systems built to listen. Deep space has vastness without density. A distress signal may travel, yes, but the physical reality of rescue is another matter. There are no nearby crews crossing the same route. No harbor lights. No chain of towns. No aerial search pattern that makes emotional sense to us. Even if Earth hears you, hearing is not the same as reaching. And in a place where reaching is almost impossible, the environment is functionally offering no help at all. This is why so much of space engineering is really the engineering of self-containment. The spacecraft must be its own air, its own water system, its own heat regulation, its own radiation shelter, its own communications platform, its own navigation platform, its own emergency ward, and often its own last chance. On Earth, the world carries part of the burden of being alive. In deep space, the burden shrinks down into the vehicle. That makes return more fragile than most people realize. Because if the spacecraft itself begins to drift away from perfect function, there is no generous environment outside it ready to compensate. If a cooling system becomes less effective, deep space does not offer a cool breeze. If a seal weakens, there is no outside atmosphere to meet you halfway. If power margins narrow, there is no nearby grid. The vehicle does not travel through support. It travels through absence. Absence does not help. And yet there is a strange beauty in this too. A severe beauty. A kind of clarity. Deep space strips away illusions about how dependent we are on context. It reveals how much of what we call travel on Earth is actually partnership with an environment. We do not simply move through the world. We move with the world's quiet assistance. Roads hold us. Air carries our voices. Gravity keeps our blood behaving normally. Seasons set rhythms. Land gives landmarks. Civilization gives repair, medicine, power, food, and memory. Once these things are removed, motion becomes something colder and more difficult than our everyday language admits. Perhaps that is why returning from deep space feels so haunting as an idea, because it is not merely a test of engines. It is a test of whether a human-built object can leave the warm web of natural and civilizational support and still remain capable of reversing its fate later, under conditions where almost nothing outside it is lending a hand. There is also the matter of scale. Deep space is so large that even opportunities to use the environment cleverly become rare and delicate. Yes, gravity assists exist. Yes, certain orbital alignments can be used. Yes, future infrastructure might one day create outposts or fuel depots beyond Earth. But those are not gifts of empty space itself. Those are carefully planned acts of engineering around a fundamentally unhelpful setting. They are ways of surviving the environment, not evidence that the environment wants you to succeed. And without those carefully arranged supports, the vacuum remains what it is, a place that lets you continue, not a place that helps you recover. You can think of it this way. If Earth is like walking through a city full of services, deep space is like walking across a frozen plain carrying your house on your back. If you get tired, the plane does not care. If you lose your map, the plane does not care. If the house begins to crack, the plane does not care. It does not hate you. It is simply not built around your needs. This becomes even more sobering when you remember that the Earth itself is moving. Home is not fixed in the way the word home emotionally suggests. It is a planet in motion, orbiting the sun at roughly 30 kilometers per second. That means return is not just about surviving the emptiness. It is about catching a moving world while managing your own motion in a vacuum that contributes almost nothing to the process. You begin to see why the universe can deny return without ever raising its voice. No monsters are required. No cosmic gate slamming shut. Just the combination of motion, emptiness, limited fuel, fragile systems, and a destination that refuses to stay still. The body, too, notices the absence of help in quieter ways. Human beings evolved inside a thick atmosphere under steady gravity, inside a biosphere full of invisible cooperation. Bones stay dense because gravity reminds them to. Muscles stay strong because Earth demands effort. Sleep cycles take shape under a sky that brightens and darkens in a regular rhythm. Digestion, circulation, balance, even the simple feeling of being physically placed in a world all emerge from this ordinary planetary support. Deep space removes much of that. Artificial systems can imitate parts of it, but imitation is not the same as inheritance. A spacecraft can provide light schedules, exercise equipment, filtered air, and carefully controlled temperature, but every one of those supports is now mechanical, not natural. It must be maintained. It must be powered. It must not fail. So even the basic human capacity to remain a healthy returning traveler becomes more precarious the farther you go. Return, then, is not just a path problem. It is a systems problem layered on top of a biological problem layered on top of an environmental problem. And through it all, space itself keeps offering the same answer. Nothing. No atmosphere to breathe. No friction to brake with. No road to reverse on. No current to follow back to harbor. No ecosystem carrying part of your load. No invisible hand of nature smoothing your errors into something survivable. Only motion, gravity, distance, and the sealed work of your own machine. If these quiet explorations help you unwind, and you enjoy falling asleep somewhere between physics and wonder, you can always subscribe and stay with the channel. And if you feel like leaving a comment, I always like seeing where these long night thoughts are reaching people. What makes this section of the journey especially important is that it changes how we should think about human ambition. We often speak as though going farther is just a matter of building better engines and being brave enough. And bravery matters. Ingenuity matters. But deep space reminds us that distance alone is not the full enemy. The setting itself is. It is a place almost perfectly stripped of the helpful qualities that make return feel natural. So a future human mission into true deep space would not simply be traveling farther than Apollo, or farther than Mars planners dream. It would be crossing into a realm where the surrounding universe no longer offers even the faint illusion of assistance. The ship would have to be its own world, its own momentum changer, its own repair shop, its own shelter, its own memory of Earth. And if that world aboard the ship is not enough, then the vast black outside will do nothing to save it. That may be one of the most honest things we can say about deep space. It is not actively trying to kill you. It just refuses to help you live, and refuses to help you return. There is a difference, but not one that necessarily feels comforting when you are far enough away. So when we ask why coming home from deep space may never be possible, one answer lies here, in the cold mechanics of the setting itself. Because return depends on support, and support is exactly what deep space does not give. It allows motion, but does not guide it. It permits survival, but does not sustain it. It contains paths, but does not mark them. It surrounds the traveler, but never joins the traveler's side. That is why the fuel problem matters so much. That is why timing matters. That is why every system aboard the ship must carry such a terrible burden. Because outside the hull, the universe is offering almost nothing. And once you are far enough away, nothing can be stronger than any obstacle. Because an obstacle can at least be fought, but an absence cannot. It can only be endured. Part 5, The Slow Limit of the Universe. There is a certain kind of hope that appears whenever people talk about the future of space travel. If the distance is too great, we tell ourselves, then perhaps the answer is simple. We just need to go faster. It sounds reasonable, almost comforting, in fact. On Earth, speed often feels like the cure for distance. A journey that once took months by ship can now be crossed in hours by plane. A message that once needed a horseback rider can now circle the world in an instant. Again and again, human history has rewarded the same instinct. If something is too far away, increase the speed, and the problem begins to shrink. But deep space is where that instinct runs into something much colder. Because the universe does not let speed rise forever. There is a limit built into reality itself. Not a technological limit. Not a limit of weak engines or unfinished engineering. A deeper one. A structural one. A limit woven into the fabric of space and time. And once you understand that, the dream of simply racing back from deep space begins to change. It does not disappear completely, but it loses its innocence. It becomes heavier, stranger, more final. The question is no longer, why don't we just go faster? The question becomes, what if there is only so fast the universe will ever allow anything to go? That is where this part of the journey begins. You can imagine a ship far from Earth, farther than any human has ever traveled, gliding through a darkness so empty it barely feels like a place at all. No nearby planet, no useful atmosphere, no road, no sound, no horizon. Just a vessel, a crew, and an idea that still glows stubbornly in the mind. Home is behind them. The way back, at least in theory, still exists. So why not point the ship toward Earth and push harder than ever before? Because harder eventually stops meaning what we think it means. This is one of the strangest lessons physics ever gave us. In everyday life, speed feels open-ended. A child on a bicycle can go faster than a child walking. A car can go faster than a bicycle. A jet can go faster than a car. A spacecraft can go faster than a jet. Our intuition learns a simple pattern from this. More energy means more speed. And more speed means less travel time. For a while, that pattern works. Then it doesn't. The reason begins with light. Light is a very unusual thing. It moves through the vacuum of space at about 299,792 kilometers per second, or roughly 186,000 miles per second. That number is so large that it almost stops feeling like a number. Light can circle Earth several times in a single second. It can travel from the Moon to Earth in about 1.3 seconds. It can cross the enormous distance from the Sun to Earth in about 8 minutes. In ordinary life, it feels instant. But in the deeper reality of the universe, It is something even stranger than fast. It is the speed limit. Nothing with mass, according to everything we have confirmed so far, can be accelerated through space to the speed of light. Not a person, not a ship, not a grain of dust, not by adding bigger engines, not by adding more fuel, not by simply waiting for better technology to arrive. The limit is not there because we are primitive. It is there because the universe is built that way. That is the first quiet blow. If deep space were just a matter of engineering, we could imagine solving it with enough effort. A larger ship, a better engine, a stronger civilization. But the speed of light is not a challenge waiting for cleverness to defeat it. It is a boundary that seems to define the rules of the game itself. And suddenly, the problem of coming home becomes more serious than it first appeared. Because once distance grows large enough, and speed can no longer rise without bound, time begins to harden around the mission. A ship going to Mars already faces this in a modest form. Even at the right launch windows, even with advanced planning, the trip takes months. Not days. Not hours. Months. A journey to Jupiter would take much longer. Saturn farther still. Neptune longer again. And these are all still inside our own solar system, still inside the Sun's gravitational family, still in what we might call the local neighborhood of the cosmic scale. Deep space beyond that begins to feel less like travel and more like duration. This is the part many people do not fully absorb when they first fall in love with space. The universe is not only large, it is large in a way that remains large even when you are moving unbelievably fast. The Voyager 1 spacecraft, one of the fastest human-made objects ever sent outward, has been traveling since 1977. Decades. And yet even after all that time, it has not come remotely close to another star in any humanly useful sense. It has left the heliosphere. It has entered interstellar space. But it is still not near another star. The distances are too enormous. This is what makes the slow limit of the universe feel almost haunting. The cosmos is not merely wide. It is wide under a speed limit. And so the dream of return begins to shrink under a very simple pressure. If you cannot go infinitely fast, then a sufficiently large distance becomes, in practice, almost the same as a locked door. The physics underneath this can sound intimidating, but the emotional shape of it is simple. As an object with mass moves faster and faster, pushing it faster still becomes more and more difficult. It is as though the universe becomes increasingly reluctant to allow it. The closer you approach the speed of light, the more energy is required for smaller and smaller gains. Not just a bit more, enormously more. The cost rises so sharply that the final stretch becomes unattainable. In a calm way, it almost resembles trying to run through a dream where the world thickens around you the faster you try to move. You still move, but the effort becomes disproportionate. Each further gain asks for more than the last. Eventually, the dream reveals its rule. There is a boundary here. You are not meant to cross it. And in physics, that boundary appears astonishingly real. This is where our old earthly habits of thought begin to fail again. On Earth, if a drive is too long, we often imagine cutting the time in half by doubling the speed. That is not how interplanetary and deep space travel works in any easy or forgiving way. Speed is expensive, very expensive. And when relativistic limits enter the picture, it becomes expensive in a deeper, less negotiable sense. Even if humanity someday builds propulsion systems far beyond today's rockets, the universe will still ask the same question. How close are you trying to get to light speed, and what are you willing to pay for that attempt? Because every increase in speed is not just a triumph. It is a cost. More energy. More shielding needs. More structural stress. More danger from tiny impacts. More consequences if anything goes wrong. In deep space, a grain-sized particle hitting a ship at extreme velocity is no longer a minor event. Speed turns even small things into threats. So the universe does not only make high speed hard to achieve, It also makes high speed dangerous to survive. A slow ship suffers from time. A fast ship suffers from energy and impact. And the return journey must somehow endure both. There is another quiet cruelty here too. Many people imagine that future technology will simply erase these concerns. But some of these concerns grow with the same progress meant to solve them. A more powerful engine may reduce travel time, yes. But if it pushes the vehicle into more extreme velocity ranges, then shielding becomes more critical, navigation becomes more unforgiving, and mistakes become more catastrophic. Faster is not merely better. Faster is more demanding in almost every way. That does not mean speed is useless. Far from it. Better propulsion could radically change what missions are possible within the solar system. It could make Mars missions more survivable. It could reduce exposure time to radiation. It could turn long durations into less crushing ones. It could open new forms of exploration and even reshape the economics of space infrastructure. But even those optimistic futures would still live inside a deeper truth. Faster is not infinite. Faster does not dissolve the scale of the cosmos. Faster does not guarantee a way home from every place we may someday reach. At some point, the human longing for return runs up against the universe's refusal to let matter move without limit. And this changes the emotional meaning of deep space in a very profound way. Because if there were no speed limit, then every distance would feel like a temporary inconvenience. Enormous, yes. Difficult, yes. But not existential. Given enough power, enough daring, enough progress, any outward voyage could be answered with an equally decisive return. Home would always remain physically negotiable. But that is not the world we seem to live in. We appear to live in a universe where time and separation are protected by law. A universe where remoteness can become more than geography. A universe where going out far enough may eventually place you beyond any return that still fits inside a human life, a human machine, or a human civilization's patience. That is why the speed limit matters so much for this story. It quietly turns deep space from an adventurous distance problem into a civilizational endurance problem. A return mission from sufficiently far away might not fail because the ship is broken. It might fail because the clock is stronger than the engine. It is worth pausing here and noticing how different this is from the fantasy versions of space travel many of us grew up with. Science fiction often shortens distance with warp drives, hyperspace jumps, wormholes, or engines that slip beyond ordinary physics. And these stories can be beautiful. They let us emotionally experience the stars as reachable, the way islands once became reachable to sailors bold enough to cross a wider sea. But in the known universe, or at least the part we have truly verified, there is no confirmed warp lane waiting patiently beyond Saturn. No tested drive that erases the years. No practical doorway through which a ship can vanish from one region of space and appear near home a moment later. There are ideas, and some are fascinating. Wormholes emerge in equations under very strange conditions. Alcubierre-style warp concepts have been discussed at the edge of theory. Physicists have played, carefully and skeptically, with the mathematics of spacetime itself. But these remain visions more than vehicles. And until they become more than that, the known universe keeps whispering the same answer. You may go outward. But if you wish to return, you must do so under the slow law of reality. There is something almost beautiful about that law, even as it frustrates us. It reminds us that the cosmos is not a blank page for desire. It has character, structure, resistance. It tells us, in the calmest possible way, that scale matters and that not all dreams can be rushed into convenience. This also means that planning a return from deep space is not only about fuel or mechanics. It is about accepting what speed cannot fix. There may be missions where the ship functions perfectly, the navigation is sound, and the crew remains brave, yet return still drifts beyond practical reach because the travel time refuses to compress enough. Distance plus the speed limit can quietly become a sentence. And the farther the mission extends, the more this fact begins to dominate all the others. Even communication lives under this same law. We touched on delay earlier, but now its deeper meaning becomes clearer. Light speed is not just the limit for ships. It is the limit for information. The same speed limit that keeps a crew from racing home also keeps advice, comfort, and human connection from crossing the gap instantly. So the mission is constrained not only physically, but emotionally and strategically. The crew becomes more alone because nothing, not even a message, can move faster than the universe allows. A ship far enough from Earth is not just distant. It is delayed in every direction. This is one reason deep space can feel so different from exploration on Earth. When a ship crossed an ocean centuries ago, the voyage was long and risky, but the Earth was still a place where winds could be known, stars could guide, and continents remained part of the same globe of human time. Deep space fractures that feeling. The distances are too large, the support too thin, and the speed limit too absolute. The farther you go, the more the mission ceases to feel like a round trip and begins to feel like a timed separation imposed by the structure of the universe itself. If these quiet journeys through science help you settle into the night, you can always subscribe and stay for more. And if you'd like, leave a comment about where you're listening from. It is oddly comforting, while talking about such unimaginable distances, to remember real places on Earth where these thoughts are landing. There is one more subtle layer to the speed problem, and it leads us gently toward the next chapter. The faster a traveler moves, the stranger time itself becomes. This is one of Einstein's most famous and most unsettling gifts to human thought. Time is not a universal clock ticking the same way for everyone everywhere. Motion changes it. Gravity changes it. Duration itself becomes less simple than common sense once believed. Now, for our purpose here, we do not need to turn this into a lecture. What matters is the feeling of what it means. In a universe with a speed limit, time and motion are woven together. The price of going fast is not paid only in energy. It is paid in the way reality itself is experienced. And yet, even that weirdness does not rescue us from the central problem. If anything, it makes it more haunting. Because a return mission may be shaped not only by the length of the path, but by the fact that time may not pass in the same way for the travelers and the people waiting at home. We will come to that more fully next. But for now, stay with the simpler truth. Deep space does not merely challenge our engines. It challenges our assumption that enough speed can always solve enough distance. The universe says otherwise. It allows extraordinary motion, yes. It allows beauty, daring, trajectory, and momentum. But it also lays down a condition. You may move through me, but not without limit. That condition changes everything. It means there are places from which, coming back soon, may never be possible. Places from which, coming back at all, may remain technically imaginable but humanly meaningless. Places where home survives as a direction, a memory, a dot of light, but no longer as a destination reachable within the terms that make return feel like return. Because if a journey takes too long, if the ship must endure too much, if the crew ages too far from the world that launched them, if civilization itself shifts while they travel, then the mission has crossed into a darker category. It is no longer simply a voyage with a delayed homecoming. It is becoming something closer to exile, even if no one intended it to be. And that possibility begins here, with a single quiet fact. The universe is large, and it is not in a hurry. Part 6. Time becomes an enemy. At first, time does not seem like the kind of thing that can hurt you. It feels too soft for that, too invisible, too ordinary. Time is what clocks measure, what calendars count, what turns morning into evening and summer into winter. We are so used to living inside it that we almost stop noticing it. We complain about not having enough of it. We waste it. We chase it. But we do not usually think of time as an active threat. In deep space, that changes. Because out there, time is not just something that passes while the mission happens. It becomes part of the mission itself. a force, a burden, a slow pressure that settles over every system, every body, every decision, every hope of return. Distance may be what creates the problem, and speed limits may be what trap you inside it, but time is what makes the trap feel real. A ship can survive a day in extraordinary conditions, sometimes even a week. A month begins to test it. A year changes the meaning of the test entirely. And when you start imagining journeys that take many years, or decades, or perhaps longer than a human life if something goes wrong, then the whole question of return becomes darker than it first appeared. Because coming home is not only about reaching the right place, it is also about arriving while home still means what it meant when you left. Imagine a crew setting out on a mission so distant that everyone involved understands, quietly, that time itself will be one of the main things they're fighting. The launch would still be dramatic. The departure would still be full of ceremony. Messages would be exchanged. Loved ones would wave. The engines would burn. The ship would rise. In those first moments, it would still feel like a journey in the ordinary heroic sense. Difficult, yes, but still recognizably human. A beginning, a mission, a return waiting at the far end. But then the years would begin to stack. And years are not like kilometers. They do not simply sit outside the vehicle as a number to be crossed. They happen inside the crew, inside the machines, inside the people waiting back on Earth. That is what makes time so dangerous in deep space. It is not external. It works on everything at once. A long mission means the human body must survive not just distance, but duration. Muscles weaken in low gravity. Bones lose density. Radiation exposure accumulates slowly, silently, in tissue and in risk. Sleep cycles strain under artificial routines. Small medical issues that would be trivial on Earth become heavier when there is no hospital nearby, no specialist, no easy procedure, no immediate evacuation. A tooth problem, an infection, a minor heart issue, a psychological collapse, anything at all that grows with time, all of it becomes more serious when the calendar keeps turning and the planet remains far away. This is one of the strange truths of spaceflight. Catastrophe is not always dramatic. Sometimes it is cumulative. A little weakness here, a little wear there, a small misalignment, a slow decline. Nothing cinematic, nothing loud. Just the body and the ship both learning, day by day, that time is not neutral. And time acts on the spacecraft no less than on the people inside it. We often imagine machines as patient and dependable, as though steel and circuits are somehow above fatigue. But machines age too, especially in harsh environments. Seals stiffen, lubricants degrade, materials expand and contract through endless thermal cycles. Electronics absorb radiation damage. Tiny fractures can begin where no one expected them. Sensors drift, filters clog. Backups that once felt reassuring slowly become the only remaining version of something essential. On Earth, age in a machine is inconvenient. In deep space, age in a machine becomes existential. The longer the journey, the more the spacecraft stops feeling like a vehicle and starts feeling like a fragile habitat trying to remain alive. Every passing month is a question put to the ship. Are you still holding together? Are your systems still within tolerance? Are your reserves still enough? Is your redundancy still real, or just theoretical now that one backup has already been used, and another is beginning to look uncertain? Time makes every earlier decision heavier. The size of the water reserve, the design of the air recycling system, the shielding around delicate electronics, the medical training of the crew, the spare parts chosen, and the spare parts left behind. At launch, all of these are engineering choices. Far into the mission, after years of use, they become the difference between hope and helplessness. And then there is the mind. Time in deep space would not pass the way time passes in ordinary life. Here on Earth, even difficult stretches are broken up by variation. A season changes. A friend visits. Weather moves through. Streets fill and empty. News arrives. Trees lose leaves and grow them back. There are birthdays, errands, interruptions, accidents, music from another room, the smell of rain, a dog barking in the distance, a random conversation you never expected to have. Earth is always changing the texture of time for us. A deep space mission offers much less of that texture. The cabin may be carefully designed. The routines may be optimized. The crew may be psychologically screened and extensively trained. But the basic reality would remain. The same walls. The same faces. The same sounds of life support and fans and electronics. The same constrained private spaces. The same scheduled meals. The same planned maintenance. The same blackness beyond the windows. Even wonder, if seen too long without variation, risks turning into monotony. And monotony does something strange to the human mind. It can flatten experience. Days begin to lose edges. Weeks blur. Memory starts to compress. It becomes harder to feel where one stretch of life ends and the next begins. This is not just boring. It can be destabilizing. People need novelty more than they often realize. Not constant stimulation, but variation. Freshness. A sense that time is moving through different landscapes rather than circling the same room forever. Without that, time can begin to feel less like a river and more like standing water. That matters because a return mission depends on psychological endurance just as much as it depends on propulsion or supplies. A crew may remain technically alive and still begin to suffer the deeper erosion of purpose, patience, emotional resilience, or trust in one another. Small irritations can grow teeth over long durations. Habits that once felt harmless can become intolerable. Silence can thicken. Grief can ripen strangely when it has nowhere to go. Homesickness, in deep space, may stop being a passing emotion and become a permanent weather system inside the mind. And unlike a storm on Earth, there is nowhere to step outside of it. That is one reason time becomes such a true enemy. It attacks from both directions. If the mission is too short, you have not reached the necessary destination or return window. If the mission is too long, the very ability to remain a coherent human crew begins to thin out. Time does not need to kill the mission all at once. It only needs to outlast your margins. There is also a more painful layer to this, one that begins quietly and then becomes impossible to ignore. While time passes for the crew, it also passes for Earth. Parents age. Children grow up. Relationships change shape. People move. Cities change. Governments change. Technologies advance. Some people who waved goodbye at launch will not be alive when the ship comes back, if it comes back at all. A crew leaving on a long deep space journey would not merely be separated by distance. They would be separated by the steady transformation of the world they hope to return to. This is one of the least discussed but most haunting aspects of long-duration travel. Home is not frozen while you are away. A sailor leaving for a year returns to a world that has changed a little. A traveler leaving for 10 years returns to something else. Push the duration far enough, and return begins to feel less like coming back and more like arriving in the future of a place you once knew. Even on a Mars mission, this already matters. A round trip could consume years. A child left behind would no longer be the same child when the traveler returned. Parents would be older. Careers would have moved on. Lives would have reorganized themselves around an absence. Deep space only sharpens this effect. At some point, the traveler is not just trying to return across physical space. The traveler is trying to return across a changing version of life itself. And then there is Einstein, waiting patiently in the background with one of the strangest truths ever discovered. The faster you move, and the stronger the gravity you experience, the less simple time becomes. Time dilation is one of those ideas people often hear about as if it belongs only to science fiction, but it belongs to real physics. At ordinary human speeds, its effects are tiny. So tiny that everyday life does not notice them. But in principle, A traveler moving at an appreciable fraction of the speed of light would experience time differently from people back home. Less time would pass for the traveler than for the world left behind. There is something almost poetic about this. You try to outrun the distance, and instead time itself begins to bend. Now, with current technology, human missions are nowhere near those extreme relativistic speeds. So for our near-future reality, this is not yet the main practical barrier. But it matters conceptually, because it reveals something profound. In the deep structure of the universe, travel and time are intertwined. The farther and faster you go, the more return stops being a simple matter of retracing your path. Even the clock comes with you in a strange, personal way. And if humanity ever did build ships fast enough to make interstellar travel feel less absurd, then this effect would become emotionally devastating. A crew might experience years while decades passed on Earth. They could come home biologically younger than the world that waited for them. The very act of returning would become a kind of temporal dislocation. That is a future problem, perhaps. But it belongs in the emotional landscape of this topic, because it shows how deep the issue really goes. Time is not merely the background of a journey into the stars. It is one of the things the stars are made of. For now, though, even without relativistic strangeness, time is already dangerous enough. Because long missions multiply uncertainty. At launch, engineers know many things. The ship's mass, the initial health of the crew, the planned trajectory, the expected performance of systems. But time introduces unknown unknowns. How will a specific crew dynamic evolve over 6 years in confinement? How will a material behave after prolonged radiation exposure plus repeated stress cycles plus one manufacturing imperfection no one knew mattered? How will a body respond to an unusual combination of isolation, altered gravity, circadian disruption, and low-level medical issues? How will a culture on board change when yesterday and tomorrow begin to lose their ordinary meaning? These are not easy things to simulate fully on Earth. We can study isolation chambers, Antarctic stations, submarines, and the International Space Station. All of that helps. But deep space is still a more total version of separation. It is not only isolation. It is isolation with irreversible distance attached to it. That word matters. Irreversible. Because time on Earth often feels forgiving. If something goes wrong, perhaps you can try again next week, or next season, or next year. But on a long deep space mission, timing windows may be narrow. Supplies may be finite. Crew resilience may be finite. Fuel margins may be finite. And if a crucial delay enters the system, time does not merely inconvenience you. It can push you out of the narrow corridor in which return was ever possible. A delayed maneuver, a slowed approach, an extended repair, an illness that forces a schedule change. Any one of these could turn months into years, and years into a mission architecture that no longer works. Time, in other words, can gradually move the goalposts while also draining your ability to reach them. This is why some of the most realistic future visions of deep space travel involve concepts that sound almost less like travel and more like managed endurance. Rotating habitats to create artificial gravity, highly closed life support systems, onboard manufacturing, medical autonomy, psychological design not just for stress, but for boredom and meaning. Perhaps even cryogenic suspension one day, if such a thing ever becomes more than speculation. Humanity keeps trying to answer the same terrifying question in more elegant forms. How do you survive a journey long enough that time itself becomes one of the primary hazards? There may also come a point where a mission stops making sense as a return mission and begins to make more sense as something else entirely. A settlement attempt, a one-way expedition, a generational journey in which the people who arrive are not the same people who left. And that possibility reveals just how completely time can defeat the ordinary idea of coming home. Because if the original travelers cannot live long enough to return, or if the conditions required for return become too costly, then the journey has crossed a threshold. It is no longer a voyage with a delayed ending. It is a transfer of human presence into a different future. That is not the same as return. It is something colder and more irreversible. If you enjoy these slow, quiet walks through science and mystery, and if they help you unwind at night, you can always subscribe and stay close to the channel. And if you feel like it, leave a comment about what part of the world you're listening from. There is something grounding about remembering Earth while talking about places so far away from it. Perhaps the saddest thing about time as an enemy is that it does not feel like one in the beginning. At launch, it still feels abundant. Even the first year may feel full of momentum and purpose. The mission is progressing. Systems are behaving. The crew is adapting. The destination, or the return arc, still lives ahead as a real shape in the imagination. But then enough time passes, and something subtle begins to happen. The mission stops feeling temporary. And once that happens, once the human nervous system no longer truly believes in the nearness of return, everything changes. The crew may still follow protocol. They may still do their work beautifully. They may still remain disciplined and brave. But deep inside, the journey begins to take on a new texture. Not one of exploration alone, but of removal. They are no longer simply away. They are in a version of life defined by being away. That is when time begins to feel less like a measure and more like a landscape. A landscape they must cross while it slowly crosses them back. And this is why returning from deep space may never be possible in the full human sense. Not only because the distance is immense. Not only because the fuel requirements are punishing. Not only because space offers no help. Not only because the universe imposes a speed limit, but because even if all those obstacles could be managed well enough to keep a mission alive, time would still remain there, patient and undefeated, asking its own difficult question. How long can a body last? How long can a machine last? How long can a bond to Earth last before it becomes mostly memory? How long can "coming home" remain the right phrase for what happens at the end? There may be no single answer to those questions. Different missions will fail at different thresholds. Some at the level of engineering, some at the level of biology, some at the level of morale, some at the level of meaning, but all of them eventually face the same quiet truth. Deep space is not only a challenge of motion, it is a challenge of duration. And the farther you go, the more return becomes a race not just against distance, but against time's steady work on everything that made the mission possible in the first place. So when we picture the traveler looking back at Earth from somewhere impossibly far away, perhaps the most honest image is not one of panic, or of dramatic danger, but of something more subdued. A growing understanding. A realization that the way home is not blocked by a wall. It is being slowly thinned by the calendar. By aging. By wear. By delay. By the patient unfolding of life in two places at once, one on the ship and one on the world left behind. And if enough time passes, those two lives may no longer fit together again. That may be the deepest cruelty of all. Not that the traveler cannot survive, but that by the time return becomes possible, return may no longer mean what it once did. Part 7, Radiation, Isolation, and Human Fragility. There is something deeply comforting about the idea that if a machine is strong enough, then the people inside it will be safe. A well-built hull, a reliable engine, a careful plan. On Earth, those things often do make danger feel manageable. We trust cars because they are engineered. We trust airplanes because they are engineered. We trust buildings, bridges, elevators, and ships for the same reason. Human life is constantly surrounded by tools and structures that help soften the world's roughness. Steel stands between us and impact. Glass stands between us and weather. Medicine stands between us and illness. Society itself stands between us and the full force of nature. But in deep space, that softening becomes thinner. The machine may still be brilliant. The engineering may still be extraordinary. The mission may still be planned with almost unimaginable care. And yet, the crew inside remains what it has always been: human, warm-blooded, delicate, biologically narrow. A species shaped by one planet, one atmosphere, one magnetic field, one rhythm of sunrise and darkness, one level of gravity, one living biosphere. Deep space does not share any of those conditions. And that is why this part of the story matters so much. Because once you move far enough from Earth, the problem is no longer only distance, fuel, speed, or time. It becomes something more intimate. A confrontation between the vastness outside and the fragility inside. The realization that the hardest component to protect on a deep space mission may not be the ship at all. It may be the people. Imagine a crew traveling outward for so long that Earth has become less like a nearby world and more like a fixed memory. The ship is still functioning. The systems are stable. The mission continues. Nothing dramatic has happened. No explosion. No catastrophic failure. Just the long, steady unfolding of life far beyond the ordinary human habitat. At first, that may sound survivable. And in some sense, it is. Human beings are capable of extraordinary adaptation. We can live in deserts, polar regions, submarines, and mountain ranges. We can work in extreme heat, bitter cold, crushing pressure, and dangerous isolation. We are not weak in the ordinary sense. We are astonishingly resilient. But resilience has context. A diver survives because a system supports the dive. A polar scientist survives because supply chains, engineering, and eventual return remain imaginable. An astronaut aboard the International Space Station survives because the station is still close to Earth, still inside the protective envelope of our planet's magnetic influence, still reachable in ways that deep space would never allow. Beyond that protective neighborhood, the terms change. One of the first dangers that grows sharper is radiation. Radiation is a word many people know, but often in a vague or cinematic way. It can sound abstract or dramatic in the wrong direction, like something that belongs to nuclear accidents or science fiction monsters. In reality, radiation in space is often much quieter than that. It is invisible. It has no smell, no warning sound, no obvious shape. It does not arrive with theatrical malice. It simply passes through matter, and sometimes through living tissue, leaving damage behind. On Earth, we are protected from a great deal of cosmic radiation by two enormous shields that we rarely think about. The first is our atmosphere. The second is Earth's magnetic field. Together, they do something profoundly gentle and life-preserving. They deflect, absorb, and soften the constant stream of energetic particles that move through space. We live beneath a ceiling of air and inside a magnetic cocoon, and because we were born into that protection, we tend to forget it is there. A crew going into deep space would be leaving that protection behind. That matters because space is not truly empty. It is filled with sunlight, particles, fields, and ancient violence still moving through the dark. Some of that radiation comes from the sun, especially during solar storms or energetic particle events. Some comes from outside the solar system entirely, in the form of galactic cosmic rays, particles accelerated by some of the most powerful processes in the universe, including exploding stars and other extreme events. These are not just abstract scientific curiosities. They are one of the most serious biological hazards of deep space travel. A spacecraft can block some radiation, of course. Shielding helps. Materials matter. Mission timing matters. Space weather forecasting matters. But shielding is not magical. Dense protection adds mass, and mass creates all the old problems of launch and fuel again. Some forms of radiation are especially hard to block without making the ship impractically heavy. And in certain cases, when high-energy particles strike shielding material, they can produce secondary cascades of particles that create their own complications. The physics becomes subtle and unforgiving. So the crew lives inside a compromise. Protected, but not perfectly. Safer than if exposed directly, but not truly sheltered in the way Earth shelters us. Over time, that matters. A long mission means a long exposure. Not necessarily enough to make someone collapse overnight, but enough to raise risks steadily, quietly, and biologically. Radiation can damage DNA. It can increase long-term cancer risk. It may affect the nervous system. It may influence cognition, mood, vision, and cardiovascular health in ways researchers are still trying to fully understand. Some effects are delayed. Some are probabilistic. Some may vary from one person to another. That uncertainty is part of what makes the problem so unnerving. Because a deep space crew would not merely be facing a known hazard with a fixed outcome. They would be living inside a field of risk that accumulates invisibly, day after day, while far from meaningful medical support. And then there is the sun. The sun feels warm and life-giving on Earth because Earth has the grace to sit at the right distance, beneath the right atmosphere, under the right magnetic protection. But the sun is also a star, and stars are not gentle by default. A solar flare or coronal mass ejection can send bursts of energetic particles streaming outward. Here on Earth, such events can interfere with satellites, communications, and power grids. In deep space, without the full protection of Earth's magnetic field, such an event could become a direct human hazard. This is one of the most unsettling aspects of radiation danger. It is not always just background exposure. Sometimes it may demand immediate action. A crew might need to retreat into a more shielded section of the spacecraft, waiting out the storm inside whatever improvised or planned radiation shelter the vehicle can provide. Water tanks, food stores, equipment placement, even waste storage might all be used as part of the shielding strategy, because in deep space every protective layer matters. You can picture the scene. No visible storm outside the window. No thunder. No rain. Just a quiet alert on a monitor. Data from instruments. A warning from Earth arriving with delay, or from the ship's own systems. Somewhere far away, the sun has become dangerous in a way the human senses cannot directly feel. And so the crew moves inward, into the safest place they have, waiting inside a machine that suddenly feels much smaller than it did before. That is the texture of many space hazards. Not loud, just intimate. And radiation is only one part of the body's problem. The human organism evolved in gravity. Not heavy gravity, not extreme gravity, just the steady, patient 1G pull of Earth. It shaped our bones, our muscles, our circulation, our sense of balance, even the way fluids settle in the body. Remove that constant pull for long enough, and strange things begin to happen. Astronauts in microgravity already experience muscle loss, bone density reduction, fluid shifts toward the upper body, changes in vision, and the general challenge of living inside a body whose old rules no longer quite apply. In low Earth orbit, these problems are serious but manageable because missions are relatively short compared to what deep space would demand, and return to Earth remains possible. In deep space, duration magnifies everything. Exercise becomes not a health bonus, but a survival ritual. Equipment must work. Discipline must hold. The crew must keep reminding their bodies, day after day, to remain prepared for a gravity that is not currently present. There is something quietly tragic about that. They would be training for a world they are not in, hoping their bodies can still remember how to belong to it later. And if their destination involves another planetary gravity, like Mars, the body must transition again. Then, perhaps, transition once more on return. Each shift is another demand placed on a system already strained by confinement, radiation, altered sleep, and accumulated time. Nothing about this is impossible in principle, but it is costly in the deeper biological sense. The body keeps paying for the journey, even when the ship appears calm. Then comes the mind, which may be the most fragile territory of all. Human beings are profoundly social creatures, even those who enjoy solitude. We regulate ourselves partly through other people, through casual conversation, through touch, through shared routines that are not officially called routines, through the subtle reassurance of being among a living world, a grocery store, a passing stranger, leaves moving outside a window, the sound of rain, a dog barking down the street, the feeling that if your thoughts become too heavy, there is still a larger human environment to absorb some of that weight. Deep space would remove much of this. A crew would still have one another, of course, and that matters enormously. Companionship may be one of the main reasons such missions are psychologically survivable at all. But companionship under confinement is not the same as life inside a whole society. In an isolated spacecraft, the number of faces is fixed. The roles are fixed. The environment is fixed. There are no accidental encounters, no change of scene, no quiet walk outside to reset the mind, no family visit, no private evening in a different room somewhere beyond the logic of the mission. Over time, this can press on a person in ways that are hard to describe unless they have lived something similar. At first, the crew might feel focused, even elevated by purpose. The mission is historic. Their work matters. Every day has meaning. But deep isolation has a way of outlasting initial meaning if there is not enough variation to renew it. What begins as calm can become monotony. What begins as closeness can become emotional crowding. What begins as teamwork can become the strain of never truly getting away from one another, even briefly, even kindly. Small tensions matter more in enclosed worlds. An irritating habit, a tone of voice, a disagreement about procedure, a private grief that one person processes inwardly and another person cannot quite understand. On Earth, many of these things are softened by the size of ordinary life. People leave the room, they take a drive, they see someone else, they walk under the sky. In deep space, unresolved tension can linger because there is nowhere for it to disperse. And yet the opposite danger also exists. Not too much emotional friction, but too little stimulation. Too much sameness. Too much quiet. Too much sameness in the meals, sounds, faces, schedules, and scenery. The nervous system can begin to flatten under that kind of repetition. Motivation can become harder to access. Emotional response can dull. The mission may continue, but the inner brightness of ordinary life may begin to dim around the edges. This does not mean a crew would necessarily break. That word is often too crude. Human psychology is subtler than that. What is more likely is a slow rearrangement of the inner world. Attention changes. Desires simplify. Memory can become strange. Time can blur. Emotional reactions may become either unusually muted or unusually sharp depending on the person and the phase of the mission. Some people may withdraw inward. Others may overcompensate with constant structure and productivity. Some may become more spiritual. Some more mechanical. Some may find deep peace in the mission. Others may carry a quiet ache that never fully leaves. And underneath all of it would be the knowledge that Earth is still there, but not truly reachable. That may be the hardest psychological fact of all. A person can endure an incredible amount when rescue, return, or reunion remains believable. But when distance becomes too large, even hope changes shape. Hope no longer means, I can go home soon. It begins to mean, I can continue. And that is a much heavier kind of hope. The crew would also have to manage the strange emotional effect of delayed communication. A message from Earth might arrive minutes later, or much later depending on distance. A reply would take just as long going back. This means no real-time comfort in moments of distress, no natural conversation, no immediate hearing of a loved one's laughter, no quick clarification after misunderstanding. Communication becomes more like exchanging letters with the past than sharing life in the present. A family problem on Earth might be known too late to emotionally participate in it. A death, an illness, a wedding, a child's growth, a political crisis, a natural disaster, all of it would arrive filtered through delay. The crew would be connected, but in a wounded way. Not absent from Earth, but no longer fully synchronized with it. That does something to the heart. And there is one more layer beneath all this. The simple biological truth that humans are not just minds riding in sealed vessels. We are animals. We need rhythms, light, cycles, freshness, texture, ground beneath our feet. Even those who love stillness usually love it as stillness within a living world. A quiet room during rain, a silent walk in winter, a sleepy house at midnight. Deep space offers a different stillness, a sealed stillness, a stillness sustained by machinery and procedure rather than by nature. It is beautiful in one sense, terrifying in another, because if the machinery falters, the stillness remains, but the life inside it does not. This is why human fragility belongs at the center of any honest discussion about returning from deep space. The mission is not only transporting mass through a vacuum, it is trying to preserve a narrow band of biological and psychological stability inside a universe that offers none for free. The farther the ship travels, the more those hidden supports must come from within. From engineering, yes, but also from discipline, trust, routine, adaptability, and the mysterious resilience of the human spirit. That spirit is real. It should not be underestimated. People have endured astonishing things. Polar winters, lifeboats, wars, long illnesses, solitary confinement, months in orbit, years of uncertainty. Humans are not fragile because they are weak. They are fragile because life itself is specific. It depends on conditions, and deep space strips many of those conditions away. So the question is not whether a human crew could be brave enough. The question is whether bravery alone can keep cells healthy, bones strong, minds clear, relationships stable, and meaning alive across a span of time and distance that pushes every part of the human system beyond the environment that made it. If these quiet explorations help you unwind, you can always subscribe and stay nearby for the next journey. And if you feel like it, leave a comment about where you're listening from tonight. There is something grounding about hearing from real places on Earth while thinking about places so far from it. Perhaps the most haunting part of all this is how undramatic it can be. Deep space does not always threaten human beings with sudden violence. Sometimes it threatens them with accumulation, a little radiation, a little bone loss, a little sleep disruption, a little loneliness, a little emotional delay, a little strain inside the crew, a little more time, then a little more. And with every passing month, the mission remains outwardly successful while inwardly becoming harder to sustain. That is often how true limits reveal themselves. Not with a single blow, but with steady subtraction. A little less margin, a little less resilience, a little less room for error. Until one day the deepest danger of deep space no longer looks like a meteor, or a mechanical failure, or even the vast distance from Earth. It looks like the simple truth that human beings were never meant to live there for long. And if that truth remains strong enough, then returning from deep space may not fail because the ship cannot find the way back. It may fail because the people inside it cannot remain fully themselves long enough to make that return meaningful, safe, and real. Part 8. Communication breaks down with distance. There is a strange comfort in being able to call for someone. Not even for rescue, necessarily. Just for contact. To hear a voice answer. To know that if something goes wrong, or if something wonderful happens, or if your thoughts become too heavy to carry alone, there is still a human presence on the other end. A reply. A pause. A laugh. A moment of recognition that reminds you that your life is still connected to other lives in real time. On Earth, we take this for granted almost without noticing. Phones ring. Messages arrive. Screens light up. A question can be asked and answered in seconds. Even when someone is far away, they still feel close because the delay has become so small that distance no longer feels like distance at all. We have wrapped ourselves in a world of near-instant exchange, and that speed has quietly shaped our emotional expectations. We have come to believe that connection should be quick, that help should be reachable, that conversation should flow without friction. Deep space breaks that illusion with extraordinary calm. Because out there, even if the technology works perfectly, even if every antenna is aligned, every transmitter healthy, every system performing exactly as designed, the message still cannot outrun the deepest rule we have already met. Nothing can move faster than light. Not a ship, not a signal, not a plea for help, not a joke, not a goodbye. And this changes everything. At first, the delays are small enough to seem almost harmless. A signal from the moon takes a little over a second to reach Earth. That is noticeable, but manageable. You can still speak and feel the living shape of a conversation, even with a slight pause folded into it. The link is not seamless, but it is still recognizably human. There is rhythm, presence, mutual timing. But once a crew begins moving into true deep space, the delay grows. And it grows not emotionally, but physically, impersonally. By law, a signal to a spacecraft 2 million kilometers away takes several seconds each way. To Mars, it can take many minutes, depending on where the planets are in their orbits. At greater distances, the waiting becomes longer still. A simple question may need so much time to travel and return that by the time the answer arrives, the original moment has already passed into irrelevance. This is the first thing distance does to communication. It does not merely slow it, it changes its nature. A conversation stops being a conversation when the pause between each exchange becomes too large. It becomes something else, more like correspondence. More like sending thoughts into a canyon and waiting for the echo, except the echo comes back shaped by another mind, not your own. And that can feel both beautiful and painful at the same time. Imagine a crew member standing inside a dimly lit spacecraft, looking at a screen with a message from home. Maybe it is ordinary. Maybe someone is talking about the weather. A child has lost a tooth. A sibling got a new apartment. A friend saw the ocean and thought of them. On Earth, these are tiny fragments of life, almost too small to notice. But in deep space, such details could become precious beyond measure. Proof that the planet still exists in all its ordinary warmth. Proof that life continues in kitchens and streets and quiet bedrooms and crowded trains while the ship keeps moving through blackness. Now imagine the reply. The crew member records a message, sends it, and waits. Not a pause of a few heartbeats. Not a slight digital delay. A real wait. Minutes, perhaps more. The human nervous system is not built for that kind of conversational stretching. A natural exchange becomes impossible. Comfort arrives too late to feel like comfort. Clarification arrives too late to prevent misunderstanding. Laughter arrives too late to join the moment that created it. And so communication begins to lose one of its most important qualities. It stops being shared time. That may sound subtle, but it is devastating. Because when people speak in real time, they do not only exchange information, they co-regulate emotion. They adjust tone. They feel each other's timing. They repair small misunderstandings instantly. They sense hesitation and ask what is wrong. They hear the softness in a voice, the tiredness, the relief. This is not decoration. It is a major part of what makes human contact stabilizing. Deep space strips much of that away. It does not erase language. It does not cut communication entirely. But it removes immediacy, and immediacy is often what makes connection feel alive. That matters during emergencies, of course. We tend to think of deep space communication in terms of crisis, and for good reason. If something breaks on a spacecraft far from Earth, there is no ability to phone home and receive instant, step-by-step guidance in the way we imagine mission control helping astronauts today. Even on a Mars mission, a serious problem may need to be diagnosed and partly solved before Earth's advice can arrive. The crew must become far more autonomous, not because autonomy is inspiring, but because delay makes dependency impossible. And this is one of the quiet thresholds that deep space imposes. At some point, Earth stops being active control and becomes delayed support. That is a very different kind of relationship. Near Earth, mission control can feel like a living extension of the spacecraft. A larger intelligence distributed across teams of engineers, doctors, planners, and specialists. The crew is not alone because a planet full of expertise is still functionally within reach. But with increasing distance, that planet begins to recede not only physically, but operationally. Advice still exists. It still matters. But it no longer arrives fast enough to carry the same psychological weight. The crew must decide more, repair more, interpret more, risk more. This is not merely a technical shift. It is an emotional one. Because when a person knows that help cannot answer quickly, the very feeling of safety changes. Even if Earth is still listening, Earth no longer feels nearby. The line is open, but stretched so thin by time that it no longer behaves like a lifeline in the ordinary human sense. There is a reason sailors once feared being too far from shore, even when the sky was clear. Shore was not only land. It was orientation, supply, repair, witness. In deep space, Earth plays that role for the mind. It is home, yes, but it is also confirmation. A place that knows you are there, knows what you are experiencing, and can still, at least in principle, respond in time to matter. Once the signal delay grows too large, that feeling begins to fray. You can see how this would change even routine life aboard the ship. A daily check-in would no longer feel like reporting to colleagues. It would feel more like sending a diary entry to the past. A response from Earth would describe a world slightly out of sync with the one the crew is currently inhabiting. Nothing dramatic, perhaps. Just enough separation to produce a subtle ache. If the mission were long enough, the ache could become part of the psychological climate on board. Because delay does not just affect problem solving. It affects intimacy. A person in deep space could still receive love, concern, news, encouragement, and memory from home. But all of it would arrive with a wound in it, a time gap. The sense that the version of the person speaking from Earth is already gone by the time their words arrive. And by the time the crew member replies, that reply is also already old when it is heard. This means that no matter how sincere the communication is, the relationship itself begins to live under distortion. Not because anyone has failed, but because reality has inserted a growing silence between each exchange. That silence would be especially painful in moments of grief. Imagine learning about an illness on Earth long after the first fear began. Imagine hearing about a death after the funeral has already happened. Imagine trying to comfort someone you love when your words will not arrive until their immediate pain has already passed into a different shape. Or imagine the opposite, the people on Earth trying to comfort the crew after a crisis on the ship, knowing that every message of reassurance moves too slowly to become true companionship in the moment it is needed most. This is what deep space does to human bonds. It does not snap them cleanly. It stretches them. And stretched things remain intact only if they can bear the strain. There is also the matter of trust in information itself. On Earth, if something confusing happens, we usually resolve it quickly. We ask follow-up questions. We correct errors. We clarify tone. We gather more context. But when each exchange takes minutes or longer, confusion thickens. A vague report may remain vague for too long. A misunderstood instruction may not be corrected until too late. An emotional message may be interpreted incorrectly simply because the natural rhythm of human repair has been lost. In deep space, misunderstanding becomes more expensive. That may sound like a minor point compared to radiation or propulsion, but it is not. In complex environments, clarity is safety. A crew and ground team working with delayed communication must be far more disciplined in how they speak, write, log, and interpret. Language itself becomes part of the engineering. You cannot rely on quick back and forth to save a poorly phrased instruction. You cannot assume a nervous crew member will naturally hear the intention behind your words if those words arrive detached from the emotional context that would normally carry them. A simple sentence from Earth might land heavily in the cabin. A simple sentence from the crew might create anxiety on the ground. And each correction takes more time. This is why deep space communication would need to be designed not just for data transfer, but for human survivability. Messages would have to be clearer, calmer, more deliberate. The crew would likely need structured communication routines, psychological support protocols, and ways of preserving a sense of relationship that are less dependent on immediacy. Recorded messages, shared rituals, carefully timed updates, maybe long-form letters, not just task-oriented checklists, maybe music, personal recordings, familiar sounds from Earth. Anything that helps carry emotional texture across distance when real-time presence is gone. In a strange way, deep space communication may begin to resemble something ancient. Not a phone call, but a letter carried across months. Not a live broadcast, but a message in a bottle. Slower, heavier, more deliberate, perhaps even more thoughtful in some respects, because delay forces people to say what they truly mean. But that slowness also comes with loneliness. You must endure the unspeaking interval after you send something important. You must live without knowing how it was received. And in a spacecraft, with the same walls around you each day, that interval could feel enormous. There is another layer to this that is easy to miss. Communication systems themselves are not simple. They require power, alignment, equipment health, software reliability, and sometimes a favorable geometric relationship between spacecraft, planets, and relay networks. Signals weaken with distance. Dishes must point correctly. Hardware can degrade. Space weather can interfere. The farther the ship goes, the more carefully the link must be maintained. So the crew is not only emotionally dependent on communication, they are technically dependent on a system that may become more fragile the more precious it becomes. That fragility has already shaped real missions. Space agencies carefully manage communication windows for robotic explorers. Deep space probes use the Deep Space Network, a global system of giant antennas built precisely because the signals from faraway spacecraft are faint and difficult to receive. Even when the spacecraft is only a machine, communication is never casual at those distances. It is a triumph of precision and patience. Now imagine layering human need onto that same system. A robotic probe can tolerate silence in a way a human crew cannot. A machine does not miss home. It does not interpret delay as abandonment. It does not lie awake replaying a message from someone it loves. It does not need to hear a human voice simply to remember what ordinary life feels like. People do. And that is why communication breakdown belongs near the center of the deep space problem. It is not only about sending commands. It is about preserving personhood across distance. A crew cut off from timely communication does not become less intelligent or less brave, but they do become more psychologically self-contained. The ship must generate more of its own emotional equilibrium because Earth can no longer supply it in real time. The crew must become, in some sense, its own society, its own audience, its own witness. That is a heavier burden than it sounds. On Earth, we are constantly reflected back to ourselves by other people. A friend notices we are tired. A partner hears strain in our voice. A stranger smiles. A coworker asks a simple question that reminds us we still exist inside a shared world. These little interactions stabilize the self. Deep space crews would lose most of them. What remains is the crew, the mission, and delayed contact with a planet that continues living without them in immediate view. This can produce a very specific kind of loneliness. Not the loneliness of being unseen, exactly, because Earth still sees you. Not the loneliness of being unheard, because Earth still hears you. Something more subtle than that. The loneliness of being heard too late. The loneliness of being seen from too far away to be held in the present. If these quiet journeys through science help you settle into sleep, and you enjoy this slow kind of wonder, you can always subscribe and stay for more. And if you feel like it, leave a comment about where in the world you're listening from tonight. It is always grounding to think of real places on Earth while speaking about distances that thin human contact so dramatically. There is also a philosophical sadness here. Human civilization is built, in part, on shared time. We celebrate together, mourn together, react together. We build trust by existing in the same unfolding now. Deep space begins to sever that shared now. It creates a situation in which the crew and the home planet no longer fully inhabit the same conversational present. They remain causally connected, yes, but not jointly present in the way that ordinary life depends on. And that is a form of separation more profound than simple distance. Because a person can survive being far away if they still feel synchronized with the world they love. A soldier overseas, a sailor on a long voyage, a researcher in Antarctica. These lives are difficult, but communication can often preserve the sense of belonging to the same living stream of events. Deep space, beyond a certain threshold, begins to interrupt that stream. The crew starts living in a pocket of delayed humanity. Messages from Earth become historical by the time they arrive. Messages sent from the ship become artifacts by the time they are heard. Everyone remains connected, but not together. That is why communication breakdown may quietly help make return impossible in a deeper sense. Not because the crew loses all contact, but because the long delays gradually transform the emotional and operational reality of the mission. Home becomes harder to feel as a living place of support. Earth becomes something watched from afar, listened to through delay, loved through silence. At first, the crew may believe that as long as the signal exists, they are still close enough. Later, they may realize that closeness and contact are not the same thing. And once that realization settles in, something shifts. The ship no longer feels like an extension of Earth's reach. It begins to feel like a world that has drifted partially outside of Earth's time. A separate island moving through blackness, carrying people who are still loved, still remembered, still monitored, but no longer held in the quick, ordinary fabric of human exchange. That is when deep space becomes truly lonely. Not when the stars look colder. Not when the fuel gets low. Not even when the distance becomes mathematically shocking. But when a human being says something important, and the universe answers by placing minutes, hours, or more between the speaking and the being heard. Because by then, the mission is no longer just far away. It is late. And a late world is not the same thing as a near one. So when we ask why returning from deep space may never be possible, communication is part of the answer in a way that goes far beyond antennas and radio waves. A crew that cannot receive timely guidance becomes more vulnerable. A crew that cannot exchange real-time emotional support becomes more isolated. A crew that can no longer share the same now with Earth begins to drift not only across space, but across experience. And once that drift grows large enough, the meaning of home changes again. Home is still there, but it is no longer within easy conversation. It is a light you can answer only slowly. Part 9, when returning stops making sense. There is a moment, in some journeys, when the original plan quietly stops being the true plan. Nothing dramatic announces it. No siren. No explosion. No official voice reading out a final verdict. The ship may still be stable. The crew may still be alive. The mission may still be progressing. From the outside, everything can appear almost ordinary, at least by the strange standards of deep space. And yet somewhere beneath the numbers, beneath the procedures, beneath the emotional instinct that has carried human explorers for centuries, something changes. Return stops being the obvious ending. That may be one of the hardest ideas to accept in all of space travel. Because as human beings, we are deeply attached to the structure of a round trip. We leave, we do something difficult or meaningful, and then we come back. A climb has a descent. A voyage has a harbor. Even war, in its saddest stories, still leaves room for the dream of homecoming. We build hope around the idea that struggle is temporary and distance can be reversed. But deep space does not always honor that shape. And sometimes, the most frightening possibility is not that return becomes impossible in some clean, spectacular way. It is that return becomes irrational, too costly, too delayed, too dangerous, too empty of meaning. A path that still exists on paper, perhaps, but no longer feels like the right use of life, fuel, time, or courage. That is what this part of the journey is about. Not the exact moment a ship is physically unable to come home, but the quieter threshold at which coming home no longer makes sense in the way it once did. Imagine a crew far beyond the familiar zones of human travel. The ship still hums softly around them. Monitors glow. Air moves through ducts. Light is measured, controlled, artificial. Earth is no longer a large and living world in the window. It is a point, or perhaps less than that, a known direction rather than a visible home. The crew has already endured the distance, the fuel arithmetic, the slow limit of speed, the wear of time, the thinning of communication, the strain of radiation and isolation. They have crossed not just kilometers, but layers of separation. And now a question begins to rise, quietly and without mercy. If they turn back now, what exactly are they returning to? At first, that sounds like a sentimental question. But in deep space, it becomes operational, philosophical, and deeply practical all at once. Because return is not free. It does not merely ask whether you want to go home. It asks what home is worth in fuel, in risk, in duration, in system degradation, in biological cost, in lost mission value, and in the possibility that the journey back could kill you just as easily as the journey outward. That is when something uncomfortable becomes clear. Return is not always the safest option. It is not always the wisest option. And it is not always the most meaningful option. We are used to thinking that going back is the conservative choice. On Earth, it often is. If a mountain storm worsens, turning back may save your life. If a boat is taking on water, heading for shore is the obvious act of sanity. But in deep space, the geometry of wisdom changes. A crew may reach a point where turning back immediately means using critical reserves, re-entering dangerous trajectories, exposing themselves to new failure windows, or abandoning the very reason they came. In some scenarios, continuing forward to a planned refuge, a station, a resource site, or even a harsh destination may be more survivable than attempting to return across an even larger emptiness. This is one of the strangest emotional reversals in space travel. Home remains emotionally central, but not always operationally favored. And that may be the beginning of the end for the old story of exploration. Because once a mission crosses the threshold where return is no longer the most rational default, it has entered a different category. It is no longer a round trip with difficulties. It is becoming something closer to a commitment, a transfer, a one-way relationship with the unknown. History on Earth gives us faint echoes of this, though never in conditions quite so severe. There were expeditions that left knowing the odds of return were low. Settlers who crossed oceans with no practical path back to the village they once knew. Migrants who stepped onto ships knowing they were not taking a long holiday, but severing one life in order to attempt another. Even soldiers marching into distant campaigns have sometimes felt the same dark intuition. There comes a point when going back is still imaginable but no longer simple enough to guide action. Too much has changed. Too much has been spent. Too much lies ahead. But deep space sharpens this into something colder. Because it is not only culture or politics or economics that reshape the meaning of return. It is physics. The equations are not sentimental. They do not care whether the crew misses home terribly or hardly at all. They simply keep asking whether the ship still has the capacity to survive a reversal, whether the timing still works, whether the bodies inside can still endure the cost. And beyond a certain point, the answer may become less and less convincing. There are several ways this can happen. One is purely material. A mission might expend enough fuel, enough redundancy, enough medical resilience, or enough structural confidence on the outward journey that the return journey no longer looks like a wise gamble. The ship might still be technically capable of attempting it, just as an exhausted hiker might still be technically capable of continuing through the night. But technical capability is not the same as sensible capability. Deep space punishes optimism that ignores margins. A crew looking honestly at their numbers may realize that the return path exists only in the way a freight bridge exists. It is there, but trusting it would be another kind of risk entirely. Another way is temporal. By the time a crew reaches a certain depth into space, or a certain duration into mission life, the return journey may no longer fit inside the meaningful span of human life or meaningful continuity with Earth. This is not just a matter of staying alive long enough. It is a matter of remaining physically intact enough, psychologically coherent enough, and emotionally anchored enough for the homecoming to still feel like a homecoming. If returning takes too long, then home can begin to outpace the traveler. Not physically only, but culturally, relationally, personally. The crew may come back to a world where many of the people who made home feel like home are gone, changed, or inaccessible. The ship may survive the return, but the original meaning of return may not. That is a subtle tragedy. It means that, can we get back? And, does getting back still mean what we hoped? Are not the same question. And missions are made not only of hardware, but of meaning. This is where the idea of one-way travel stops sounding reckless and starts sounding, at least in some circumstances, brutally honest. We often hear one-way missions discussed as if they belong only to desperation or science fiction. But in truth, many futures of space expansion may depend on them in one form or another. The first humans to go far beyond Earth's comfortable reach may not be explorers in the old sense. They may be more like permanent transfers of human presence. The first crew to establish a distant station, a settlement, or even a fragile outpost may do so without any credible short-term plan of returning to the planet that launched them. Not because no one values them, but because physics has made the alternative too expensive. This possibility tends to disturb people, and understandably so. It sounds harsh, almost cruel. And yet when you sit with it long enough, it becomes clear that deep space may not care whether our emotional imagination prefers round trips. If humanity ever goes far enough, and stays long enough, we may find that the old model of exploration breaks apart. You do not always go there and then come back. Sometimes you go there and become part of there. That is when returning stops making sense most completely. When the mission is no longer about visiting distance, but about inhabiting it. You can picture a future crew approaching a remote destination after years of travel. Perhaps it is not another star. Perhaps even that dream remains far beyond us. Perhaps it is only a far-flung station in deep solar orbit, or a long-duration habitat beyond the inner planets, or a hard-won foothold in some isolated region where resupply is rare and return more fragile than propaganda once suggested. The crew arrives tired, altered, older in mind if not always in body. They have crossed too much to remain what they were at launch. And now Earth asks, or perhaps merely hopes, will you come back? But maybe the wiser answer is no. Not because they do not love Earth. Not because they do not miss it. But because too much has already been reorganized around the outward commitment. The station needs them. The mission needs continuity. The return vehicle is not ideal. The resources are better used building permanence than funding nostalgia. The crew itself may understand that another multi-year transit, another great crossing of empty time, would cost more than it restores. In that moment, staying may be less a tragedy than an adaptation. That is what makes this topic so psychologically difficult. We are not just confronting danger. We are confronting a redefinition of success. On Earth, success in exploration often means making it back and telling the story. In deep space, success may eventually mean not coming back at all, because the only meaningful way to justify the cost of going is to remain, build, transmit, continue, and let Earth become a place of origin rather than a place of return. That would mark a profound shift in human identity. For most of history, even when people migrated permanently, the world was still one world. Different continents, yes, but one planet, one sky, one biosphere. Deep space threatens to divide the human story into separated habitats whose connection is real but slowed, fragile, and expensive. A person born in one place may spend the rest of life somewhere else not merely by choice, but because return no longer makes practical sense. Distance creates not just remoteness, but divergence. And once divergence begins, return becomes more complicated than travel. It becomes translation. Re-entry not only into gravity, but into an older self and an older world that may no longer fit. This also raises a moral question that deep space missions cannot avoid forever. At what point is it honest to tell people that a mission is technically reversible but practically one way? We have a deep instinct to soften truth when ambition is involved. To say that options remain open, that contingencies exist, that return is planned even if it is uncertain. But deep space may punish that kind of comforting language. A mission that has crossed the point where return requires too much luck, too much sacrifice, or too much empty endurance should perhaps be named more truthfully for what it is. Not a round trip, a departure. There is dignity in naming things clearly. A person can commit to a difficult truth more honestly than to a beautiful half-truth. The first crews who eventually leave Earth for destinations too deep, too harsh, or too long to sensibly return from may deserve the respect of precise language. Not heroes promised a way back that exists mostly in optimism, but pioneers stepping knowingly into a future where home changes shape. That may sound bleak, but it does not have to be. Because one way does not always mean hopeless. Sometimes it means the mission has matured beyond tourism, beyond a symbolic flag-planting gesture, beyond the emotional need to reassure ourselves that every journey can be folded neatly back into the old world. A one-way commitment can be the beginning of continuity, of presence, of a new branch of human life learning how to exist somewhere that was once only a point of light in the sky. The sadness lies not in the absence of return alone, but in the cost of understanding why return no longer fits. And that understanding may arrive gradually. A crew member might first feel it while reviewing resource projections late in the mission. Another might feel it while listening to delayed messages from Earth that no longer feel immediate enough to sustain the old fantasy of going back unchanged. Another might feel it while watching the ship age and realizing that even if the structure survives, the emotional architecture of homecoming is eroding faster than anyone admitted at launch. Another might feel it in a very simple way, standing alone near a viewport, looking at the darkness, and realizing that the years needed to undo this journey would consume the years left in which undoing still means anything. That is the threshold. Not necessarily when return becomes impossible, but when it becomes hollow. A return that empties the mission. A return that consumes the crew. A return that arrives too late to restore what was lost. A return that exists in the language of mission planners, but no longer in the reality of lived human meaning. Once a mission reaches that threshold, continuing forward can become the more honest act. This is also why settlements, permanent habitats, and generational thinking may become central to any real future of deep space humanity. If return loses practical meaning beyond a certain range, then missions must stop imagining themselves as giant versions of Apollo. They must become ecosystems, places, commitments that plan for staying rather than merely surviving transit. food systems, psychological design, maintenance cultures, education, medicine, governance, memory, ritual, even art, all of it would matter because the mission would no longer be a visit. It would be the beginning of local life. And local life changes the arithmetic of return. A person who leaves Earth to help build such a place may no longer ask only, "How do I get back?" They may begin asking, "How do we make this place worth remaining in? How do we make distance livable? How do we transform exile into home?" That may be the deepest human answer to a universe this large. Not to outrun the problem of return, but to outgrow the assumption that return is always required. Still, none of this erases the ache. Even if a one-way future is rational, even if it is noble, even if it is necessary, it does not stop being emotionally difficult. Human beings do not simply detach from Earth because a mission briefing says they must. We carry origin deeply. Sky, weather, gravity, smell, language, touch, memory, all of it gathers into the feeling we call home. A crew who chooses not to return, or cannot meaningfully return, would still live with longing. They might build new routines, new communities, new rituals, even new forms of joy. But longing would remain like background radiation in the soul. Maybe that is why this topic feels so heavy. Because it suggests that the future of deep space humanity may not be a future of heroic out-and-back adventures, but of sorrowful maturity. Of accepting that some distances change the moral shape of travel. That some journeys, once undertaken, are not really journeys in the old sense at all. They are transformations. They turn travelers into residents, explorers into caretakers, missions into lineages. If these quiet reflections on science and distance help ease you into sleep, you can always subscribe and stay for the next one. And if you want to leave a comment, I always like hearing where on Earth you're listening from tonight. There is something strangely reassuring about real cities, real rooms, and real nighttime routines while thinking about places so far from them. Perhaps the most honest way to say all this is very simple. There may come a point where the best way to honor a deep space mission is not to bring it home, but to let it become what it has already become. Not a trip. A new condition of human life. And that possibility forces us to rethink courage itself. Maybe courage is not only the willingness to leave. Maybe it is also the willingness to accept when return no longer fits the reality you have entered. To release the old symmetry. To stop pretending that every frontier behaves like a coastline that can be crossed twice. Because the universe is not arranged for our narrative comfort. Some distances allow return. Some allow only delayed return. And some, if we go far enough, may quietly ask for something more radical than either. Not a temporary separation, but a permanent rerouting of human life into places that do not forgive easy homecoming. That does not make the journey meaningless. If anything, it may make it more meaningful. Because then the crew is no longer just proving that humans can endure distance. They are proving that humans can survive the loss of the old idea of return and still choose to build, to continue, to create significance where none was naturally provided. And maybe that is what deep space has been asking all along. Not whether we are brave enough to go, but whether we are honest enough to admit that if we go far enough, the question will stop being how we come back. It will become who we are willing to become if we don't. Part 10. Could humanity ever solve the way back? After everything we have considered, it is natural to end with one final question. Is there any real hope? Not the soft kind of hope that ignores physics. Not the kind that appears in movies whenever a last-minute engine comes online and the crew escapes the impossible. Something calmer than that. More serious. More honest. Could humanity, with enough time and enough intelligence, ever solve the problem of returning from deep space? Could we build a future in which the dark between worlds is no longer so final? It is a beautiful question, partly because it carries two different emotions at once. The first is longing. The simple human wish that no matter how far we go, home should still remain within reach. The second is humility. The understanding that the universe may not care what we wish, that it has its own scale, its own laws, its own silence, and that our dreams must either fit inside those laws or change shape. So perhaps the most honest place to begin is this. There may never be one single invention that solves the way back. No miraculous engine. No universal key. No clean moment in history when human beings look up and say, at last, distance is defeated. Deep space is too large, and the problems are too layered for that. Fuel, time, biology, radiation, communication, psychology, infrastructure, orbital mechanics, all of them remain part of the story. Solving return will likely never mean erasing all those problems at once. It will mean, if it happens at all, learning to reduce them one by one, until some journeys become survivable that once were not. That is a more modest hope. But modest hope can still be powerful. Because when people imagine the future of spaceflight, they often picture a single dramatic breakthrough. A warp drive. A wormhole. A ship that somehow steps outside ordinary physics and leaves the old limits behind. And perhaps one day, some idea we can barely imagine now will open a door that seems impossible today. Human history is full of surprises, and it would be foolish to pretend the future must remain small simply because the present is incomplete. Still, if we stay close to what is grounded, the likelier answer is slower and more complex. Humanity may not conquer deep space by finding one miracle. We may do it by building layers of capability until the return journey stops being absurd in some regions, even if it remains nearly hopeless in others. In other words, the way back may be solved locally long before it is solved universally. And that distinction matters. Returning from the moon is already hard, but it has been done. Returning from Mars may one day be done, though it will demand a level of planning, infrastructure, and resilience far beyond Apollo. Returning from deeper regions of the solar system may remain so punishing that only robotic missions make sense for a long time. And returning from true interstellar distances, from the kind of space between stars that our imagination loves but our engineering still fears, may remain beyond meaningful reach for much longer, perhaps longer than we comfortably like to admit. So the answer may not be yes or no. It may be, some of the way back can be solved, but not all of it. One path toward that future is better propulsion. This is the most obvious answer, and for good reason. Faster ships mean shorter trips. Shorter trips mean less radiation exposure, less system wear, less accumulated psychological strain, and less life spent waiting in transit. If humanity ever builds propulsion systems that are dramatically better than chemical rockets, then many of the burdens we described earlier begin to ease, even if they do not disappear. Nuclear thermal propulsion is one example that has fascinated engineers for decades. In simple terms, it could allow spacecraft to achieve better performance than conventional chemical rockets by heating propellant with a nuclear reactor rather than relying only on chemical combustion. The details are technical, but the underlying hope is easy to understand. More efficient propulsion could shorten travel times to places like Mars and reduce the amount of propellant needed for the same mission profile. That alone could be transformative. Nuclear electric propulsion offers another route. It can provide efficient long-duration thrust, especially for cargo or deep space operations, though usually with lower raw thrust than chemical systems. Fusion propulsion, if humanity ever manages to tame fusion in a practical and controlled spacefaring form, could go even further. It remains more dream than vehicle for now, but it lives in that interesting middle ground between fantasy and serious speculation. Then there are concepts like solar sails, beamed propulsion, and other elegant ideas that try to borrow momentum from light itself or from remote energy sources instead of carrying all the burden on board. These ideas remind us that ingenuity in space does not always mean building a bigger engine. Sometimes it means changing the whole architecture of the problem. Still, even the most optimistic propulsion ideas do not abolish the deeper truth. They may make the solar system more reachable. They may make return from some missions more realistic. But they do not repeal the speed limit of the universe. They do not make interstellar space small. They do not erase the possibility that some journeys will remain too long, too risky, or too costly to bring people back in the ordinary human sense. So propulsion helps, but it is not the whole answer. Another path is to stop imagining a spacecraft as a single heroic object and start imagining the larger system around it. This may be even more important than the engine itself. For most of human spaceflight, we have treated missions as self-contained events. You launch from Earth, you carry almost everything you need, and you either come back or you do not. That model works for nearby missions, but it does not scale well into deep space. If humanity wants a genuine way back from farther regions, then we may need to do what humans have always done when expanding into difficult territory. We may need to build infrastructure. Not only ships, but routes. Not only courage, but support. Imagine a future in which Earth orbit is full of depots, maintenance platforms, assembly yards, and transfer stations. Imagine the Moon not only as a destination, but as an industrial partner, a place where fuel can be produced from local resources, where materials can be processed, where missions leaving Earth do not have to drag every kilogram up from the deepest part of our gravity well. Imagine Mars missions supported not by a single enormous launch gamble, but by layered systems, pre-positioned supplies, fuel production on the Martian surface, orbital staging platforms, and robotic preparation long before the crew even arrives. The phrase for this is often in situ resource utilization, which sounds technical but describes a very human idea. Use what is already there. Do not carry everything if local materials can help you survive. The Moon may contain water ice in permanently shadowed craters. Mars has carbon dioxide in its atmosphere and water in various forms. Some asteroids may one day serve as sources of metals or volatiles. If those resources can be turned into fuel, air, water, building materials, or shielding, then the return journey becomes less impossible because the outward journey no longer carries the entire future on its back. That is how civilizations usually solve distance. Not by building one perfect vehicle, but by filling the route with support. A ship crossing an ocean is easier when there are ports. A traveler crossing a continent is safer when there are towns. Deep space may need its own equivalent of that old human pattern. Habitats, depots, relays, automated factories, fuel plants, repair nodes, navigation beacons, sheltered transfer points. Piece by piece, the emptiness would become less empty. And that may be one of the deepest shifts in the human relationship with space. The way back may not be discovered. It may be constructed. Of course, that still leaves the human body. Even if propulsion improves and infrastructure expands, the basic fragility of biology remains. So another part of solving the way back may involve learning how to protect and preserve the body much better than we can now. Artificial gravity is one possibility. Instead of asking human physiology to tolerate years of weightlessness, future spacecraft might rotate, creating a gentle centrifugal effect that mimics some aspects of gravity. This has long appeared in science fiction, but it is also taken seriously in various engineering discussions because the body does not easily forget what planet it evolved on. If artificial gravity can reduce bone loss, muscle atrophy, fluid shifts, and other physiological stressors, then long missions become more survivable, and return becomes more plausible because the crew arrives less damaged by transit. Radiation protection must also improve. Better shielding materials, smarter spacecraft layouts, active shielding concepts using magnetic or electric fields, real-time space weather forecasting, dedicated storm shelters inside ships, all of these may matter. Some solutions may be partial, some heavy, some costly, some still theoretical. But even partial protection changes the equation. The goal may never be perfect safety. It may be survivability with margins that are no longer absurdly thin. Closed-loop life support is another essential piece. If a ship can recycle air, reclaim water, manage waste, and perhaps even grow some of its own food with high efficiency, then long-duration missions become less dependent on endless stored supplies. The ship becomes less a fragile container of diminishing reserves and more a small, managed ecosystem. Not a true Earth, of course. Nothing like that. But a better imitation than current spacecraft can provide. Onboard manufacturing may help too. A crew that can produce replacement parts, medical tools, simple structures, or repair components using stored raw materials or recycled waste gains a measure of autonomy that older missions lacked. A broken system becomes less likely to mean mission collapse if the ship can make some of what it needs instead of merely inventorying what it already has. Then there is medicine. A deep space crew would need far more medical independence than any astronauts have ever had before. Remote guidance from Earth is useful only up to a point, and communication delay changes everything. So future missions may depend on crews with broader medical training, advanced diagnostic tools, robotic assistance, compact surgical capability, regenerative therapies we do not yet fully possess, and perhaps AI systems able to help identify problems early, model risks, and suggest interventions when human specialists are too far away to function as true real-time support. That brings us to artificial intelligence itself, which may play a larger role in solving the way back than many people first expect. AI will not repeal physics. It will not magically erase distance. But it could help manage the astonishing complexity of long missions. It could monitor life support systems continuously, predict failures before they occur, optimize trajectories, assist in repairs, personalize psychological support, manage medical data, and preserve operational discipline when the crew is tired, emotionally strained, or isolated. A deeply autonomous ship supported by sophisticated AI may not make deep space easy, but it could make it less dependent on fast communication with Earth. In a place where delay turns human support into something slow and wounded, machine assistance may become a crucial form of local stability. And yet even all of this may not be enough for the longest journeys, which leads to more radical possibilities. One of them is suspended animation, or something like it. Humans have long fantasized about sleeping through deep space, allowing the body's needs to slow while the ship continues. True cryosleep, in the science fiction sense, does not exist for humans. We cannot simply freeze a person for years and wake them unchanged. Biology is far more difficult than that fantasy suggests. Still, scientists continue exploring forms of torpor, metabolic slowing, and other ideas that might one day reduce the burdens of long-duration travel. If a future crew could safely spend large portions of a journey in a greatly reduced metabolic state, then many constraints shift. Food demand drops. Psychological strain changes shape. Some medical risks may lessen while others emerge. The mission stops being lived moment by moment in the ordinary sense and becomes something stranger, a voyage punctuated by waking rather than continuous endurance. That remains speculative, but it points toward an important truth. Solving the way back may require changing not only the ship, but the human experience of the journey itself. Another possibility is even more radical and, in its own way, more sobering. Humanity may solve deep space continuity not by ensuring that the same people who leave always return, but by creating missions in which return is handled across generations. A generational ship is one of the oldest and most haunting ideas in long-range space travel. A vessel so self-contained, so durable, and so socially complex that one generation leaves and another arrives. In one sense, this solves the problem of duration. Human life continues. The mission continues. But in another sense, it reveals just how thoroughly the old idea of return has dissolved. The people who come back, if anyone ever does, are not the same people who left. The journey becomes less a mission than a moving civilization. That may sound remote, and it is, but it forces us to think clearly. Some solutions to the way back may only solve continuity, not homecoming. They preserve human presence, but not the old symmetry of leaving and returning within one human life. And maybe that is where the deeper answer lies. Could humanity ever solve the way back from deep space? Yes, perhaps, for some kinds of deep space, for some distances, for some missions. Within the solar system, especially if we build enough infrastructure and advance propulsion, life support, radiation protection, autonomy, and medicine, the answer may increasingly become yes. Not easily, not cheaply, not soon enough to feel casual, but yes in principle, and eventually yes in practice. Beyond that, the answer becomes more complicated. For very distant missions, for the emptiness between stars, for regions so far that even extraordinary propulsion leaves time as a crushing enemy, the way back may remain unsolved in the old sense. Not because humans stop trying, but because the universe is not required to make every dream returnable. Some missions may still be possible, but only as one-way journeys, settlement efforts, generational transfers, or symbolic acts of endurance rather than true round trips. And that is not failure. It is just a different relationship with reality. Because the future of deep space humanity may not depend on preserving the illusion that every frontier behaves like a nearby shore. It may depend on learning which journeys can remain round trips, which can become supported routes, and which require us to let go of the old idea of return entirely. There is something strangely peaceful in that thought. Not easy, but peaceful. It suggests that maturity in space will not come from refusing limits. It will come from understanding them clearly enough to build wisely inside them. We will solve some problems, not all. We will shorten some journeys, not abolish distance. We will protect the body better, though never perfectly. We will communicate more intelligently, though never faster than light. We will bring home what can be brought home. And for what cannot, we may learn to build new forms of human belonging far from Earth. If these slow reflections help you relax into the night, and you enjoy wandering through these quiet cosmic questions, you can always subscribe, leave a like, or share a thought in the comments about where you're listening from. There is something comforting about knowing these ideas are landing in real homes on one small planet while we imagine places so far beyond it. In the end, the way back may not be one thing. It may be a ladder. The first rung is better rockets. The next is better habitats. Then shielding. Then medical autonomy. Then fuel made away from Earth. Then stations, depots, manufacturing, artificial gravity, smarter ships, stronger crews, and perhaps one day deeper alterations in how we travel through time, sleep, and distance. Each rung brings some journeys back within reach. Each rung turns a little of the impossible into the merely difficult. But the ladder may not reach everywhere. And that is the final calm truth this journey leaves us with. Deep space is not a puzzle that guarantees a neat solution. It is a vast reality that asks different things of us depending on how far we dare to go. In some directions, humanity may eventually build a reliable way back. In others, we may only build a way onward. And perhaps wisdom is knowing the difference before we leave. So maybe the real question was never simply whether we can come back. Maybe it was whether we can become the kind of species that knows when to return, when to stay, and when to admit that the stars are not asking for visitors at all, but for patience, preparation, and a very different kind of courage. Because the universe may one day let us travel farther than we ever imagined, but it will still ask, quietly and without emotion, the same question at the edge of every mission. What have you built that can survive the distance? And if the answer is enough, then perhaps some crews will come home. If not, then the future of humanity in deep space may begin the way many futures begin, not with a return, but with a decision to remain.